First, start with some housekeeping rules. So we have both in-person and remote attendees. The remote audience are muted throughout the session. And if you have any questions, please post them on Zoom, and we will ask on your behalf. And if you are in person, please hold your question and ask at the end of the talk at the mic there. And because we have a very tight schedule, we will have very strict timekeeping. And for the speakers, we will remind you 2 minutes before the time is up. And then if you run over time, we have to interrupt. All the keynotes and oral talks will be recorded and shared afterwards. And for in-person attendees, please don't join the Zoom session so that we can save the conference bandwidth and also allow more people to join remotely. For this morning, we have 4 very exciting talks and also a poster session. The talks will cover a range of topics from the fundamental techniques to applications to image, video, 3D, and art. And you are also more than welcome to join the poster session where you can talk with the audience about the latest advance on AI for content creation. So next, let's welcome Lingjie to introduce our first speaker. Lingjie, are you there?
Hello, can you hear me? Hello? Hello? Hello?
Yes, we can hear you.
Oh, great. Yeah, thanks. Hi, everyone. I'm Lingjie Liu from UPenn. Now, let me introduce our first speaker.
Lingjie, can you unmute yourself? You are.
No. Hello?
Well, I
Hello?
can hear Lingjie.
Oh. I think people can hear over Zoom, but not in. Wait, thanks.
Lingjie, can you speak again?
Hello?
Yeah, it works.
Thanks. Hi, everyone. I'm Lingjie Liu from UPenn. Now let me introduce our first speaker, Ben Milhon. Ben is at Google, where he works on problems at the intersection of graphics and computer vision, focusing on view synthesis and inverse rendering. He completed his PhD from UC Berkeley in 2020, advised by Ren NG and supported by a Hetz Fellowship, and received the ACM Doctoral Dissertation Award honorable mention, and the David Serial Memorial Prize for his thesis work on neuroradiance fields. He has received a paper award at ECCV 2020, ICCV 2021, CVPR 2022, and ICLEAR 2023. Actually, I don't think Ben needs an introduction, as he is very well known. He has done a lot of pioneering work in neural fields and 3D generative models, such as nerve, gene fusion, MIP-nerve, RAF-nerve, etc. I have followed up his work for a long time. Yeah, so now, Ben, please start your presentation.
Okay, testing for the Zoom again.
Good, we can hear you.
Thanks. Okay, so this particular example is kind of a good, it's a good example of what we were able to achieve in the original NERF work for results on real scenes. We kind of had these forward-facing limited windows into a scene instead of like a full 360-degree capture. Okay, so that's where we started, and where have we gotten to now 3 years later? One of the main focuses we've had in our group is extending NERF to capture full, rich, immersive 3D environments rather than just that kind of limited window into a scene. So nowadays, when we go out and capture a scene, it looks something like this. We'll take a camera, we walk around for like 10 minutes, capture about 1,000 pictures to get good coverage of a large environment. And from that data, we're able to create really, really nice large-scale 3D reconstructions of scenes. This is a fly-through rendered from a NERF of the data captured in the previous video. And of course, it's not just something you can use to bake out static videos. They just had me unmute because the Zoom was not here. Okay, so now. Okay. Let's get you better. Yes, it's me. Thanks. Okay. All good now? Yeah, still, okay. Right, so just recapping NERF very quickly. As I said before, we start with a set of input images and camera poses. In training or test time, we sample 3D points along rays through pixels in those input images. Then we query some underlying consistent 3D scene representation for the color and opacity values at each of those points. We use volume rendering to composite them down into a single RGB output for the pixel, and we optimize an underlying re-rendering loss versus those input pixel colors. And this turns out to be a sufficient constraint to us to recover a pretty decent 3D reconstruction of the underlying scene if we have enough pictures. And we were able to do this for kind of full 360-degree object captures in the original NERF work, but only for synthetic objects. And most of our real world results, again, look like this kind of limited forward-facing window into the world. We did have 2 360-degree results in the original work, but there's a bit of a kind of a sneaky trick in here. So both of these scenes are rendered with the camera facing down towards the floor with the horizon not really visible. And that's because the reconstruction is only good in kind of a limited window around that central object. And this leads directly into the line of work I want to discuss first, on how we were able to extend NERF to actually work in full unbounded 3D environments. So for us, this started with MIP NERF 360 from CVPR last year. And this was really focused on this specific problem of a central object and then a rich, detailed 3D background behind it, where you were assuming usually a kind of capture where the camera is rotating around the object. And there were two main issues we found extending our previous work to these large scenes. The first one we had was the scene parameterization. So because unbounded scenes are unbounded, you kind of face this issue where if you're putting these query points through an MLP or even some grid representation, you really need those to be in a bounded coordinate space for the capacity of your underlying model to be allocated well. And another problem we faced was that these large scenes have so much more like textural and geometric detail than a single object. And you can just naively extend the size of the MLP or your underlying representation, but then it turns out, obviously this just requires more and more compute and makes your network much slower. Okay, so to fix parameterization, let's take a look at how we did this in kind of like a top-down 2D view of a flatland scene with 3 cameras. So if we trace out these 3D points from the cameras, we can see that they kind of get more and more stretched out farther away from the camera views. And in this specific instance, I'm showing these kind of ellipses instead of points because this builds on our previous work that extended NERF to consider not only single points in space, but kind of like a Gaussian volume approximating conical frustums to help combat aliasing issues in original NERF. Okay, so we have these Gaussian footprints, and what we want to do is we want to squeeze and compress them down to some bounded volume of space. So we use a warping function that is identity inside the unit sphere, but rescales points as a function of 1 over their norm outside the sphere. And we end up with all of our points inside the sphere of radius 2, which is kind of a much nicer situation for the underlying MLP to deal with. And to deal with the size of these Gaussians, we can just track the Jacobian of this warping transform and just apply it to the covariance matrices to modify how they've been warped. So the second problem was increasing the capacity of that underlying NERF network without causing a huge slowdown. If we increase the size of NERF, we have to reduce the number of samples per ray to get a constant compute budget. But now this means that where we place the samples becomes more and more critical. And if we just naively uniformly sample along the array, we're always going to miss something. So to fix this, we introduced this idea of a proposal network that tells you where in space you should allocate your samples along the array. And its output is in the form of density, which can be normalized into a probability distribution, like as shown by the green bars here. So we can take that distribution, resample new points from it, and use those as the rendering points in 3D to compute the final color along the array. And as this proposal network converges with the NERF, it kind of acts as a sort of continuous acceleration structure that tells you where the most important parts along the array are to place samples. So the reparameterization and the proposal network together allow us to allocate samples well, even with a very large underlying NERF network, and achieve high quality reconstructions with not too much computational cost. This is an example, 360 scene with renderings of color and depth maps to show that the geometry is also quite nice. But at this point, even with the proposal network speed up, we're still hitting over a day to train, even on Google cluster resources. So this is not great. But after we were working on this, NVIDIA introduced this crazy paper with an amazing speed up for training NERF from a matter of seconds for a 360 synthetic object and maybe a few minutes for like those forward-facing scenes. And this was all based on using hash grids as a spatial data storage. And the issue we had with scaling up MLPs is that their runtime just linearly increases as you increase the number of parameters. So every point that you query through the MLP ends up touching every single parameter of the underlying weight matrices. And this is obviously not great as you want to reconstruct bigger and bigger 3D scenes. The nice thing about the hash grids or any kind of spatial data storage is that you only need to query the model by touching a couple parameters. As you make the scene bigger or the model bigger, you're not touching more and more parameters. You're just doing this kind of like spatial lookup that's effectively constant time in the size of the model. However, switching to this kind of spatial grid model, we lost that ability to deal with Gaussians that MIPNERF and MIPNERF 360 had. And we ended up seeing results like this where we didn't have great aliasing properties. So you can see there's a lot of shimmering in like the bike spokes here as the camera's moving back and forth. In our latest project, we wanted to address this problem and reconstruct very large scenes by anti-aliasing a combination of instant NGP and MIPNER 360. So I won't go into too much detail here. At a high level, we basically upgraded the samples here from a single point sample to multi-samples that aggregate features gathered from multiple points across the NGP grid. And we found that this very effectively anti-aliased the bike spokes in this example and many other artifacts we saw. There was also another source of instability that was directly related to the proposal network we'd introduced in MIPNER 360. So it turned out that this network itself can kind of alias back and forth. So if you move the camera into the scene and away again, even that uniform distribution of samples you put through the proposal network can easily miss thin foreground structures. And you can see this in this real example from a NERF trained with the original proposal loss. The blue histogram here is from the first round of proposal sampling, and it kind of jumps from the foreground to the background object as the camera moves slowly into the scene. And you get this like crazy artifact sweeping through the thin structure of the chair as a result. So if we focus on 2 frames here, first, this is kind of a mistake frame with an error at the green cross pixel. In this case, all of the proposal samples were allocated to the background column, so it's inevitable that we're not going to hit the surface in later rounds of sampling. But if we push the camera in a little bit, now we're at a pixel that was rendered correctly. So here the proposal network put all of its weight in the foreground, and then it's subsequently sampled well in the later networks. So in ZipNerf, we proposed a fix for this problem by essentially pre-blurring or anti-aliasing the weight distributions for the proposal supervision. And this results in a much more stable distribution as we sweep the camera forward in the z-axis. So here you can see that the kind of first blue round of proposal sampling is blurred out. It's no longer quite as tightly focused on a single histogram bin, and it actually allocates some samples to both foreground and background, but then later higher resolution representations are able to correctly discern which of the objects is the right one to hit for the ray. Okay, so combining all these things together, this is a comparison with kind of like the original naive baseline method we implemented, combining MIPNER 360 and instant NGP, versus on the right, our full method with all of those changes. So it's a little bit subtle, but you can kind of catch a few of these striping artifacts and like floaters in the panel on the left as the camera goes through the scene. There's a couple particularly bad ones on these chairs, I think. Yeah. So our model is basically an improvement fixing up the issues with this baseline to achieve nice results on large scale scenes. This is one of my favorite captures from this project. This is a cafe in the Google New York office. Again, this whole capture is only about, I think, 1,200 pictures. And the underlying representation, the NGP weights and the MLP are 300 megabytes in total. So we're able to effectively kind of compress this whole scene, all this detail into 300 megabytes, and then we're able to re-render it freely. And since it's a full 3D representation, so we are not limited to just rendering out these, perspective camera paths. In this case, this is actually a 360-degree video I rendered out and put on YouTube. So you can load that up on your phone or your computer and navigate around, like freeze frames and change the viewpoint at any frame in the sequence. And this 360-degree rendering idea is actually being used to power a new feature that Google Maps has launched very recently. This was Sundar announcing it at Google I/O last year, and it's finally started to roll out, I think, almost 100% now. And there's a few restaurants that you can load up and get this kind of 360 pano video and navigate through on your phone. Okay, so that's kind of one extreme end of the trade-off of quality versus speed. That New York cafeteria video took 2 hours to train, but actually 7 hours to render because it's such a high-res video sequence. And that's because it was around 12 seconds per frame, again, across 8 V100s. And this is roughly 5,000 times too slow for real time on a single GPU. So what are we going to do about that? We'd really like to have more practical and affordable methods for rendering trained NERFs with reasonable hardware constraints. So this brings us to 2 recent projects we had last year. We had 2 interns with us in the Google London office who ended up both exploring complementary approaches to making real-time view synthesis tractable, starting from a NERF-like representation. So for some context on the framing of these 2 works, obviously we have ZipNerf as kind of an upper bound, like a gold standard for the quality we can expect to achieve with unlimited time and compute. The first project kind of moves in from the left here, asking, okay, we want to preserve as much quality as we can. We want to keep a volumetric rendering model, but we want to make it fast and tractable. And the second project said, okay, we're going to give up as much quality as we need to achieve absolutely, totally manageable and affordable speed on any consumer hardware. And the approach there was kind of starting from, okay, we're going to go to a triangle mesh because that's what we can render really easily and portably. But how little do we have to give up to get to that trade-off? So the first work, MERF, basically is a combination of 2 gridded 3D representations. So there's a sparse 3D grid and then kind of a higher res triplane representation used to model texture. And we found that this point in the kind of trade-off for memory and compute achieved pretty nice quality. And here, this is still an underlying volumetric rendering model. So this is basically just, like a kind of fiddling around, tuning parameters until you find a nice volumetric NERF representation that can be baked out and rendered quite quickly. These are results rendered on real time on a single 3090. So we're able to hit that target of 60 FPS on reasonable consumer hardware. But on the other hand, 3090 is not necessarily in the hands of everyone out there. So it's not something we can just share as like a web demo and expect to run on phones or things like that. And the other problem on our end is that getting this level of performance in a portable way requires implementing some pretty horrible shader code in WebGL or OpenGL. So this kind of narratively leads into the other work. So Baked SDF is living on top of a mesh, so it can bootstrap itself on existing rasterization pipelines. And the way we get the mesh is we start with one of these hybrid surface volume reconstruction methods. It's kind of an in-house combination of Ball SDF and MIPNER 360. That gives us a nice starting geometry proxy. We bake that out, and then we just optimize effectively a surface light field on top of that mesh. So this is the underlying mesh geometry you get for that garden-based scene I was showing before. This is pretty clean. It's sort of better than what you get with Column Map. Nice flat surfaces on the table and decent geometry in the background. And existing on top of this kind of mesh means we can support a final pipeline that allows for real-time rendering on basically any commodity device, again, just by making use of existing super fast rasterization pipelines. And that underlying model we use for the surface light field is based on a combination of a diffuse color and a couple spherical Gaussians for view-dependent appearance, which means we can have this nice interpretable visualization of the specular component of the scene as well. And the shader code for this is super, super simple. Since we're just effectively writing a new fragment shader, all we have to do is pass forward all of our spherical Gaussian parameters and write like one really simple function like this to evaluate the final color. Okay, so again, why do we have 2 different papers that have almost the same title and attack the same problem? The takeaway here is that Baked SDF is a lot easier to implement and it's faster and cheaper, but it's a little bit lower quality because we sacrifice the volumetric rendering to go to the final mesh representation. Whereas MERF preserves that underlying volume rendering model, but it requires significantly more flops in total. And there are actually real-time demos for both of these methods on their respective websites. I'm posting the MERF link here since Christian has made some really nice compressed versions of the scenes that you can even load pretty easily on a phone, maybe on the conference Wi-Fi, probably not. Okay, so moving on to one final project in a bit of a different, more kind of purely creative direction. This is Dream Fusion, which Ben Poole presented at iClear just a couple months ago this year. Again, so going back to normal NERF, we have this underlying re-rendering loss function that expects a set of input images that we're trying to match with the 3D reconstruction we're doing. But what if we had a loss that could actually evaluate an image without any kind of ground truth reference? What if we had a loss that could just tell you how well that image matched an input text prompt? So this is obviously something we can try to do with the amazing developments that have happened in generative models recently. And this was all based on kind of plugging in a diffusion model as a loss for supervising NERF. So, of course, at Google, we have access to like really nice generative 2D image models like Imagine. This is an example result for a photo of a peacock on a surfboard. And we're lucky enough to have access to these as kind of like a black box to use to train 3D or distill 3D models out of. And the way we did that was a method called score distillation sampling. So just in brief, this is kind of a way of turning the underlying sampling process of the diffusion model into an image-based gradient that can be used to supervise NERF based on, kind of the direction that the generative model thinks you should move the image to best match the underlying text prompt. And by using that to supervise NERF, you get this final 3D asset out at the end of training. Okay. So I'll walk through the process of the rendering pipeline here and the training loss. So, okay, first of all, we're no longer limited to a finite set of input images. So we can actually freely randomly sample any camera we want and render the view from that point. And it's not only just extrinsic pose, right? We can change focal length. We could even change camera model. We didn't do that, but you can get a really nice, diverse, augmented set of input images around the object since you're just randomly sampling views. So this is, again, kind of a per scene optimization based method. Every new 3D model, we run this optimization procedure again. So there's one underlying NERF MLP for each of the objects we generate. And instead of outputting RGB color directly, we actually output effectively a Lambertian albedo. And since it's just an albedo, we need to shade it to get a final image color. So to do that, we take the analytic normals from the density field as geometry. We take a randomly sampled point light. We do n.l to get a kind of shading quantity to multiply against the albedo. And that gives us our final shaded color. This produces our 2D output rendering. We feed this through a single step of the diffusion model. And this gives us kind of an update image direction. And if we take the difference from that and the original NERF rendering, we can treat that as like an image-based gradient that we should backpropagate onto the NERF representation ways. And that is the process of a single optimizer step. So every step we have to render a whole image and do this diffusion step and then backpropagate the output. We repeat this for 10, 15,000 steps. It takes like an hour or so, and it produces this final sort of relightable asset in that it has albedo, and you can move that point light around and get different views. And something we found was quite critical for getting nice geometry here was the fact that we used that factorized shaded representation that had an albedo and a normal dotted with a light direction. So this effectively backpropagates onto the normal through the diffusion model, and that actually kind of supervises the underlying geometry to become much cleaner. So in a normal NERF, you expect a lot of kind of fog and weird artifacts, but because you're moving around this point light and augmenting the renderings by changing the shading, it actually effectively smooths out the normals and makes the underlying geometry much more kind of usable as an asset. So here's a very long sequence of results. I think there's 415 videos that we created for the website for the project. And the thing to think about here is that like this model is supervising these underlying NERFs on randomly sampled views at all points in a 3D hemisphere. And there's essentially no chance that all of those views are in distribution for the model, yet it's still able to reconcile all of those views in a kind of consistent way and produce these nice 3D results. We were inspired by the Dolly website to make this kind of choose your own adventure tree of results for our page. I had to pre-create, 150 squirrels for this and choose them all by hand. But now, as a result, you can go through and select this. We found that you kind of lose some of the creative power of the 2D model. Like our loss is essentially a little bit mode seeking. So it's a little biased to work better on things where the diffusion model has like a very strong conceptual idea of the underlying idea you're trying to generate, and it often will drop multiple constraints. In this case, we found that squirrels worked much better than I think panda bears and dogs and some other animals, and squirrels were much better at picking up on all of the the modifiers to the prompt. Yeah, just as with VolSTF, you can bake out a mesh here, which shows that geometry is not terrible. People actually 3D printed a lot of these frogs. The chicken, I think the geometry is a little too fine. But yeah, these are being rendered with Google's like model viewer HTML embed. It's super simple code. You just export a GLB file with the geometry and the per vertex colors, and then you can have this nice interactive viewer that works on any device easily. All right, that concludes all the stuff I wanted to cover in the talk. And of course, you know, immense thanks to all the collaborators who have worked on this. These projects are basically all the Baked STF and MRF were intern projects by Lior and Christian. John was lead author on ZipNerf and MITNER 360, and we were working with Ben and Ajay on Dream Fusion. And, oh, that's on the wrong slide. And yeah, you can find project pages and more at my website for all these works and our other NERF-related projects. And happy to take any questions.
Thank you very much, Ben. Are there any questions in the room? There are 2 microphones set up in the aisles here, and we'll also take questions from Zoom. So I have a question for Ben. It seems like we've solved all of the problems. So what is there still to solve in this area?
Yeah, I had a slide that I took out of this talk that basically ended by saying all of this is kind of fancy tech demos, so none of it is real and robust yet. So I'd say that's kind of the main thing. You know, I mean, for these large scenes, like a lot of these things hold up on, you know, rendering these nice quick fly-throughs, and you just don't look at them too carefully. But if you're really like doing like an interactive viewer and inspecting stuff, you can very easily find places where things fall apart. I think for the kind of like view synthesis angle, we capture the scenes we can do, right? And then we show results on those scenes. And you essentially can't do anything very shiny, very see-through in the real world, because it's just like, it's too hard right now. And our models kind of fail, and the optimization-based methods with the like current representations we have exploit all these little like cases to make fuzzy geometry, like weird floaters that pretend to model complex specularities, but don't really. On the 3D generation front, I think this is, you know, we've seen like a bunch of improvements to Dream Fusion in the last 6 months already. I think this problem, there's still underlying fundamental problems with using the 2D models for this, in that they don't know about like the idea of a single 3D consistent model. We see this multi-head thing. You know, we made 400 models for the website, but probably generated 4,000 to get those. It's very cherry picked. And you get that kind of like prompt engineering skills, you do it. So you try to ask for things that you know it can do well. Yeah, and I think also, yeah, portability in terms of like having clean geometry, having disentangled materials and lighting and things like that is still very, very early days, essentially, yeah.
Thanks, Ben. We have a question from Zoom on the more technical side. MIPNERF compares itself with a brute force super sampled NERF. Is it fair to say that ZipNerf resembles a version of a super sampled NERF?
Yeah, I mean, I think essentially that is the case. So there's one difference in that, like, purely super sampled NERF, I would consider to be shooting multiple rays per pixel and then averaging those colors. ZipNerf is slightly cheaper than that because we average the multi-sampled features before feeding them through the MLP that still exists at the end of instant NGP. That actually speeds it up quite a bit and reduces the total memory footprint. I think there maybe is, I don't remember if there's a full super sampling baseline in ZipNerf, but it's a similar direction, and it's kind of what you're forced to do once you go to this explicitly gridded spatial data structure, right? You have to do like some filtering or some multi-sampling, but yeah.
Great. We have a question in the room. Here, please.
Hi. Right. Not working. I just have turned it on. I turned it. It's on? Oh, right, okay. Okay, hi, thanks. You mentioned about those different types of nerve for dream fusion, like albedo and lighting kind of things. Could you share your experience working with it on nerve setting other than so? Or if you haven't, could you share your thoughts, maybe guesses? What will happen if we use those kind of albedo and lighting things in those common nerves?
Mhm. Right, yeah, so our group has looked a tiny bit into this, right? Bertold did nerve a few years ago that was kind of like a factored nerve with a BRDF under known lighting. And there's been a ton of other research groups who've worked on this. I think it's if you assume unknown materials and unknown lighting, you're very, very under constrained in a way that makes you kind of fall into local minima very, very easily. I think we've seen some pretty good recent progress on this, but still mostly in the realm of synthetic objects, just because, you know, there's all these extra ambiguities you get when you're solving for both of those at once. And the really nice thing about dream fusion is that you're not trying to match a single set of observed images under some unknown illumination. You just change the illumination yourself and it's just data augmentation, right? So it's kind of like, it strengthens that method, but it weakens regular methods in that, like, oh, the geometry can really get messed up. Like essentially losing the assumption of just like a pure multi-view constraint with a little bit of specularity that you get with regular nerf for just view synthesis, and actually asking for full disentanglement makes the problem much, much harder and more unstable, I think.
Okay, and we'll take one more question, this time from Zoom. Sorry, people.
No.
For dream fusion, how does the underlying diffusion model know how to handle renderings of different views if the input text is fixed?
That's a good leading question. I glossed over this in the talk, but it's actually not a single input text prompt. We augment the text prompt based on the angle of like the azimuth and the elevation we sample from the hemisphere for the camera pose. So we'll augment it with front view, back view, side view, top view. And this is kind of slippery slope for us. We experimented with like very, very top view or like super side, super stuff like that. You know, all the usual things you expect with text diffusion models, because you can totally change the output of them with prompting. And one of the things we found that most improved results was appending DSLR photo of, or wide angle DSLR photo of, which we discovered a day or two before the deadline, very kind of tragically for our academic minds. It's not a great feeling when that improves your results a lot, but yeah, so I think that's a big gaping hole, essentially exploiting the fact that these models are aware of how objects look from different viewpoints, but you're not embedding it into the text prompt very carefully or precisely, or it's just this hand-done heuristic thing. Right. Yeah, I think so.
All right, Ben is able to hang around for the break, so if there's any remaining questions, please catch him then. But let's thank Ben again for the very engaging talk.
Try to get better geometry out of like scale scenes using their to try to compete with like MBS. Yeah. What do you think is like the more important
Zoom people, can you hear us? Zoom folks, can you hear us okay?
Yes, we can hear you.
Boom. All right. So just mute your output. John, are you ready to introduce Ryan?
Yes. Okay, yeah. Hi, everyone. This is Yijun from Adobe. I'm glad to introduce Ryan Murdoch, my colleague, who is a machine learning researcher and engineer at Adobe, interested in multimodal generative systems. Throughout 2021, Ryan released a number of open source text-to-image notebooks that highlighted the potential of leveraging feature visualization techniques on multimodal neural networks to perform text-to-image. He advocates for natural language-driven generative systems as a new and promising medium of art with the potential to force reassessment of how we view art, minds, and automation. Ryan, take it away. We cannot wait to hear your talk.
Thanks so much. I'm really excited to be here. I didn't expect the ceiling to be as cool as it is. So, and thank you for that. Awesome. Thanks. Oh. Awesome. Thank you. So today I'm going to be talking about some of the social considerations of generative models. When I talk about generative models today, it'll be scoped as generative models that are used for creative tooling. And it'll apply to some degree to a number of models, but in mind, I have large scale text to image models in particular. So you can think of this as sort of an overview. I'm gonna make some arguments during it because I just can't resist, but we'll start by talking a little bit about generative creative tools as learning not just data, but also culture. I'll move into representational bias and some insidious feedback loops that are potentially there. I'll touch on disinformation and misinformation, and I will then talk about the hot button issue of licensing of training data and ownership of it. Then I'll talk about generative models as an artistic medium themselves, automation concerns just broadly, and then directions for mitigations and a conclusion. So this list isn't exhaustive. There are other social considerations, but I'm going to touch on some that I think are particularly important or particularly spoken of. So one thing that I think most of us probably know here as practitioners is that the design of our models can be very simple, while their behavior can be kind of unexpected and hard to interpret. And given those two things, I think that we should have some concern over our models being used for increasingly significant decisions in some ways that are very explicit, like determining whether we think that someone is eligible for welfare, along with some more subtle ways. And I'll be talking about things that are subtle, but I think still fairly significant and impacting uses of these models. So I'll start by reading a quote by Ted Underwood. He's a humanities professor, and speaking to language models in particular, he says that these models are clearly not modeling language in a sense that would be separable from content. What they really are is culture models. And I think that this is applicable to basically any model that we use in this creative tooling generative sense that's learning from human data. about human things. And so I also think that this is doubly true at web scale or at large amounts of data. So an example that I always give, because I think it's kind of like sweet and kind of bizarre at the same time, is that Janelle Shane, around the time of like GPT-2, GPT-3, was prompting this language model, GPT either 2 or 3, I forget the specific version, and asking it how many eyes a horse has. And it was responding with anything ranging from like 0 to 16 eyes, which obviously is not the case. And so there were lots of questions about like, well, is this because it lacks embodiment? Is it not grounded enough? Does it just need, you know, the modality of vision? And so when CLIP came out and I was kind of like early days looking at some of the things that it could do to drive generative models to do text to image, I decided to try inputting a horse with 4 eyes. And to my like sort of shock and like amusement, it produced this horse wearing glasses. And I thought that was just the like sweetest, weirdest thing that it could have done. But I think it also highlights that these models are learning things that we care about. It's not just that we're learning about images or text, we're learning about this particular ideas that are intrinsically social and cultural. And it even goes so far as you can think of these models as sort of meta art. For instance, with Midjourney, people talk about it as being aesthetically opinionated. And you can usually recognize the outputs of such models that are kind of pushing the aesthetics of the outputs, especially by the default in certain specific ways. And so you can think of that as almost being a collaboration between the people creating and making design decisions and the people using these models. But some of those stylistic decisions quickly become more than just about aesthetics. For instance, if you ask what a beautiful person is or what an angry person looks like, there's some clear instances where aesthetics are more than just aesthetics alone. So one thing that Mario Klingemann, who's an artist kind of in this machine learning art space, along with generative art broadly, one thing that Mario Klingemann says is being an artist in a time of visual abundance might be more about what you do not put into the world, only that attention has a blind spot for what is not there. And so I think that we need to think about sort of the default assumptions and sort of default, like in a kind of specious sense, opinions that these models might have. So Alison Parrish, who is a machine learning researcher and poet, has, I really think, very, very eloquently described the idea that data and models and programming and all of these different things are a form of forgetting. She says that in the process of programming or scanning or sampling or digitizing or transcribing, much of the world is left out or forgotten. Programming is an attempt to get a handle on a small part of the world so we can analyze and reason about it. But a computer program is never itself the world. So there's this kind of idea that data itself is only going to be able to capture so much about the world, and our models are similar. And so I think that means that we need to think about and be careful about who and what we're forgetting. So we all know that our models that too are, you know, kind of generative creative tooling often have biases in terms of things like what groups they'll assign to occupations, what groups they'll assign to even emotional valence, and just general stereotypes. And I think that these representational biases have, you know, clearly some very serious material consequences. For example, you can imagine hiring bias being a huge issue that has very significant impacts on the lives that people lead. And I think that feedback loops between things like, for example, representation of occupations and the actual groups within those occupations can be really something very serious. For instance, if you think that, you know, nurses are most commonly women, men may be less likely to go into that field, and then it sort of cements that bias in the real world, which is pretty serious. And that's why I think that it goes representational bias in our models beyond just forgetting about people, because we would expect that because the data itself is forgetting some aspects of the world, we would expect even with a well understood kind of filtered licensed data set that is just ideal, we should still expect bias from it, because not only do our algorithms enhance bias, like with Style-Gans truncation trick, leading to more racial bias in its output of faces, but we also, even with perfect data, should expect that we're going to represent some of the bias in the real world. So I think that we ought to avoid that and represent the world in ways that don't create these kinds of insidious feedback loops. I used to talk a lot about models as being kind of like mirrors onto ourselves and our cultures and the internet and things like that. But I think that once we've deployed our models, they're much more analogous to billboards, where we're kind of setting descriptive, normative standards, and that can be like really powerful and really detrimental. And I also think that just pragmatically, people who are deciding to take kind of the other route and releasing models of like today's like quote unquote realities, I expect them to be embarrassed when those realities change. And that's why I think it's just very important to think forwardly about how we see people in our models. So I'm really quickly going to touch on disinformation and misinformation. There have been a number of like really exciting, promising methods for not just image models, but even text models. And I think that that is, on the one hand, really exciting and really important, but I also think that because we can imagine people not immediately being able to identify watermarks, and because we know that on the dynamics of social media, we often have some false information come out that gets a ton of attention with a correction that gets very little attention. I think we also need to be thinking about like this idea of generative media literacy and treating images as sort of just like text, where they are not trusted by default. So training data rights and ownership is something that I think a lot of people are very, have very strong opinions on. But I think that in principle, there is a very long precedent within art, and arguably a necessary thing within art, of taking public information, synthesizing it, and creating something new. And you could even argue this is the case in many other domains. We can consider collaging, fan art, pastiche, and many other artistic modes as all necessarily entailing this. And one counterexample that people often come up with is that our models are less apt to be able to do attribution than we are, which I think is a little bit incorrect. Like you can take, for example, that if you're deciding to draw a ghost, you've probably never seen a ghost, I would hope. And so as a result, you're obviously relying on the images that you've seen that have been created by people when you create that image of a ghost. And if you aren't being explicitly thoughtful about it and trying to reference someone, I don't think that you'll be able to pick like the top 5 candidates for which ghost influenced your ghost. I don't think that it's very realistic to say that these models that we can do similarity search on their data sets for and all of that are much worse at doing attribution than we are. Although obviously when someone is explicitly referencing something within a prompt or when they're doing art themselves, that is a different thing entirely. So I also think that many of the proposed solutions or mitigations for this are kind of bearing some risks along with them that can be pretty serious. This involves like no guarantee of improving model behavior. I think that if we actually are interested in improving the behavior, we should be doing careful audits. And it also has the effect of cutting off many researchers and just the broader public from these new ways to create imagery that and I think that like essentially you're saying, well, if you can afford to buy the data, which some people can, you can have access to these models and these capabilities. And I think that that, if anything, should deepen concern over the economic effects of these models. Not to mention that traditional artists would be, pretty severely threatened if it became possible to like have ownership over a style, which I think is on its face kind of silly. So fundamentally, I think that this is primarily about the jobs. You could imagine a model that's from fully licensed and owned data, posing some of the same concerns to artists, even if they've not been included in that data and have opted out and everything else. So while I think that there's not a lot that's new to these models in principle, I think the scale and effect is obviously a big deal. And it's reasonable that people raise alarms about this. So the next thing I'll touch on is this idea of wondering, like, can these models create art? And I suspect that everyone here sees these as tools that can create art, but I think that it's good to explicitly go over like why our intuition may be that you can create art with these models. We can consider like just many, many different ways of creating art, ranging from poetry to photography to painting and so on. And I think we need to delineate between what is craft and what is art, because you can have different skill levels for all of these things, but you're doing different things with each of them. And what is necessary for art can't vary between all of these different things. And you can also think about some instances of like edge cases of really simple actions that don't require any specific craft or skill that are very widely considered art, like Duchamp's fountain, which was a urinal that was put in a museum, is like kind of the pinnacle of modern art. And I think that that kind of is an interesting edge case for showing what is artistic might depend more on our intentions and whether it comes out to be compelling rather than some specific mode of creation. I also think that the increased accessibility to creating new and having easy access to existing mediums and genres is also like a really compelling thing about these tools. I think that in my opinion, it's clearly something that's good for art broadly. The last thing I'll say before I move on to economic concerns is that I think that it's important to delineate when we're discussing art as this sort of romantic concept and art as this sort of like image making industry, because like the two obviously have significant overlap, but I also think that we can feel kind of cynical talking about the like bottom line and the financials of it, but I think we still have to have that discussion. So there are historic analogs to these large-scale generative systems, ranging from like drum machines and synthesizers in music to the camera. And Aaron Hertzman notes in a paper that we don't really regret the camera, but when we think back to the initial advent of that technology, people were very worried about it and concerned, which is, I think, an important analog to these models today. On the other hand, I also don't think that we should just sigh and point to issues like at the macro level and be like, oh, well, I mean, it's capitalism. We can't solve this. We need to, do X, Y, Z else. I think that we kind of have to grapple with the trade-off that's being made here. I think that, especially when these models are made fully accessible and either commodified or open source, I think that it's very much a worthwhile artistic and economic trade-off in exchange for the concerns that these models raise. But I also do think that a change at the systems level so that we didn't have to worry about every time we make something easier or more accessible, like we're raising competition and making people fear for their jobs. So where do these issues leave us at? I think that research into fairness and bias and debiasing is like really, really vital. I also think that, pushing to actually use the current mitigations is really important. I think one of the main things that prevents these mitigations from being implemented is just a lack of understanding, like what would an ideal model even look like, and So I think that we, as many of us are practitioners, need to be pushing for this, because it's easy to say it's hard and just not do it, but it's important. I also think that open audits are really something that we should be targeting. Like if we're concerned about the behavior and effects of these models, I think that audits are the way to actually directly attack that versus policing of training data and similar things like that. And then for disinformation, I think that detection is important, but I also think just education in terms of not trusting images and treating them as if they were text is also very, very important. And as automation continues, I think that eventually we will get to the point where industries that don't have this sort of like human capital to them are going to be affected. And so I think that that's going to be very, very worrisome when, for instance, like office jobs become more automated. I think that that will be a different conversation, but I think that the uniting thing between all of these different industries is that we want to see productivity gains shared. And I think doing everything that we can to ensure that at the level of doing open source work and making sure our products are accessible is one thing. And even at the macro level, I think we need to be sure that we're pushing for shared productivity, especially when productivity becomes much more available with these models. So in summary, our models are learning more than just data. They're learning about culture. We need to really take on representational bias and disinformation. And I think that ownership of data is not a panacea like we might want to think. And there's a lot of work to be done, but that's in some ways pretty exciting. Thank you.
Thank you very much, Ryan. Are there any questions for Ryan in the audience from this thought-provoking conversation? Hello.
Hello, hi. Thank you for the talk. I think it's very interesting and important topics. I just was wondering, what is your impression of the things that are being done right now in industry and academia about all the concerns of this field?
Yeah, I mean, I think that in industry and academia, I honestly think that we're making some strides. I can think of some papers like the Sega paper and some of the learning to forget style of papers that are really promising in terms of representational bias and harms in particular. I don't see them getting implemented a lot of the time, which is kind of concerning. And I think it like an institutional level like needs to be taken care of, because I do think we have a lot of tools for mitigating these issues, and I think we're not using them as much as we should. So yeah.
I have a question for Ryan. Recently, there's been lots of debate about how fast industry is moving into this space. I wondered if you had any thoughts about whether it's too fast, too slow, perhaps?
Yeah, I mean, I think that the biggest thing that I can think of is trying to kind of take these machine learning systems and have them do things that we know that they can't do. I mean, for instance, we know that these models sort of hallucinate, and we also are trying to use them for search. And so I think that it's maybe not moving too fast in the sense of like creating them, but moving too fast to deploy and productize them. I think that we need to be mindful about how people will actually use these tools and what they'll think they're actually doing. So.
Any further questions for Ryan? All right, let's thank Ryan again. We will now take a short break. Ryan and Ben are here at the front if you'd like to come and say hi. And we will start again at 10:20 with Angela Dye and Tim Salomons talking next. Thanks, everyone. See you soon. Okay, people on Zoom, can you see and hear?
Yes.
Thank you very much. So our second session, we are pleased to introduce first Professor Angela Dai. Angela is an assistant professor at the Technical University of Munich, where she leads the 3D AI group. Angela's research focuses on understanding how the 3D world around us can be modeled and semantically understood. Previously, she received her PhD in computer science from Stanford and her BSc in CS from Princeton. And Angela's research has been awarded an ERC starting grant. She's been awarded the Eurographics Young Researcher Award, Google Research Scholar Awards, amongst other things, topped off by an ACM SIGGRAPH Outstanding Doctoral Dissertation Honorable Mention. So I'm very excited to welcome Angela to our workshop here. Let's welcome Angela.
Thanks for the very kind introduction. Happy to be here to talk a bit about generating 3D models. So in my group, we're very interested in reconstruction and capture of real environments, for instance, from commodity sensors like iPhone RGB video or RGBD video these days, and understanding the underlying geometric structures behind these environments, for instance, for content creation or mixed reality kind of applications where we want to be able to emulate the appearance and physical properties of real inspired objects in virtual environments, as well as for imbuing machines with the potential to perceive the world similar to how we as people do. So I wanted to talk a little bit about the history in terms of 3D reconstruction, just from a very broad overview, that when I started my PhD, we were very heavily focused on optimization for 3D reconstruction. For instance, bundle adjustment, call map. These methods had remarkable success in terms of optimizing for camera poses and the 3D representation of a scene that's being observed by a collection of images. But then, of course, we discovered the power of deep learning and how we can potentially learn strong geometric priors for things like unobserved regions that we haven't actually captured in these input images. And these are difficult to achieve without having this knowledge of data-driven priors of what objects typically look like, from the other side, if seen only from one view. Of course, now, and you've seen earlier today already, we've come a little bit back to the 3D reconstruction as optimization with neural radiance field optimization from multi-view image optimization. So I wanted to talk a little bit about how we can potentially combine the learned priors from data along with optimization for various kinds of content creation purposes. So in particular, we're taking a look at the task of texturing 3D shapes. So in this case, the learning is going to take place in terms of trying to learn a plausible manifold of shape textures. So given an input kind of shape geometry, can we propose a manifold where if you sample from that manifold, it produces a plausible kind of texture on that shape. Then given, an input query like an image as inspiration, we'd like to search in that manifold and try to find a texture that best represents perceptually the input image hopefully to serve as kind of inspiration for this kind of artistic texturing purpose. Now, there's a few challenges here in terms of the learning, which is that given that we're heavily data-driven, we want to look at 3D data and what's available in terms of textures. At the moment, we have things like ShapeNet, and the textures on these kinds of 3D objects are not very realistic. On the other hand, we have 2D data that's available as images, which give photorealistic representations, but without any notion of 3D or even multiple views of the same object, just one view of various kinds of objects with highly realistic imagery. So our goal here is to take a given input shape geometry and learn a manifold where we can sample and produce arbitrary kind of reasonable textures on the input geometries. And then, because we want to be able to sort of navigate this manifold through some kind of guidance, our guidance is image queries. So take a photo of an existing object from the real world or a photo online and try to produce a texture on the geometry that is representative of the image query without assuming that we have any knowledge of the geometry underlying that image structure or the pose, since this should be reflective of real world kind of scenarios where we don't know anything about the geometry or the pose really of the objects being observed. So we first learn this texture manifold. We have the input shape is being given into the encoder along with the latent code that should represent the texture being applied. And we're going to produce features on a per face basis on this mesh in the input shape. The input shape is basically a quad mesh, and we can then produce a feature map that lives one feature per face on this object, which we can then differentiably render to the image domain so that we can compare it with the real images that we have in the training set. Here, since colors are living on a per face kind of basis, resolution is pretty limited since we can't infinitely just create artificially high resolution on the mesh. So we also use a local neural field that's going to interpret the per face features in the coordinate system, the barocentric coordinate system of the faces, and that's going to produce high resolution colors on the surface of the shape. So here, in contrast to the volumetric representations, we're actually attaching color values to the surface of the 3D shape. So what that looks like in a bit more detail here, we have all of the shapes as quad meshes. And we want to be able to leverage this power of sort of the developments in 2D convolutions, a lot of which has been this nice kind of properties of translational equivariance, as well as the ability to do hierarchical upsampling and downsampling. So we try to apply the same kind of principles on the 3D shapes, and this is based off of a previous work, Texturify. So here you see the hierarchy of shapes, where we start with a very coarse cube approximation of the shape, and we can pre-compute this hierarchy at various different resolutions that are all quad meshes of the same shape. And that allows for the pooling, upsampling and downsampling kind of operations on the mesh faces. And then because we're operating on a quad mesh, we can set the maximum number of neighbors and use that as the neighborhood for the convolutional operator that lets us take a StyleGAN2 inspired encoder and generator on the level of the individual faces, imagining them kind of as pixels in an image. And so that gives us the per face features on this shape. So once we render these out, we also going to render out the high resolution and refined features and colors from the local neural field. And that's going to give us the ability to really compare high resolution generated imagery to real images. And this is being formulated in an adversarial fashion because we don't have any known correspondence between the geometry that we're working with and the images that we're working with. So we just want to ensure that the textures being applied are similar to the real distribution of images. We have a proxy loss also on the course version, and that's just helping with the convergence of the training here, so that we don't have to learn everything solely from the high resolution local refinement. And going through this optimization, we can learn a nice kind of texture manifold where, given some kind of input shape geometry, we can then sample arbitrary texture codes and produce the colors on the surface of these shapes. So here you can see, this is actually kind of cool that we can learn colors on the whole of the shape, actually given only examples of single views of individual objects as real images. On the other hand, considering that we model only color and not necessarily the rest of the image formation process, you do get like lighting effects and reflections and stuff in the car windows baked directly onto the surface of the objects. So once we have this manifold, then we want to be able to optimize for a texture based on an input image query. And so since we don't assume that there is an exact correspondence in geometry here, we're just going to take a look at how well perceptually the textures that we produce and the image query look at the level of patches. So this is going to be a bit more robust to differences in geometry, and we can use a VGG-based style loss at the patch level in order to optimize for the desired kind of texture on the manifold that looks perceptually similar to the image query. So these are a few examples with the image query on the left. And the optimization process is being visualized over several iterations as we try to find some shape texturing that will match with the given query image. So we can take a look at this both for the unconditional texturing, not conditional on the input query image, as well as based on the transfer from the query image. This is just sampling arbitrary textures from a bunch of different state-of-the-art methods. And the main challenge here is effectively learning the distribution from just single image views of objects. So the adversarial formulation here, along with the ability to resolve that high resolution locally on the surface of the objects, helps us get nicer, sharper kind of texturing on these shapes than some nice state-of-the-art alternatives. We can also transfer textures from RGB image queries that you see here. So here there's no correspondence between the geometry. The real images are from ScanNet images for the chairs and from comp cars for the cars. And so, of course, we don't try to go too wild in terms of the differences of geometry. At some point, the patch level reasoning might break down, but we can actually transfer the same kind of concepts to relatively different kind of shape geometries and get the same basic idea of, this wooden chair with a red seat applied to a different type of chair shape. But it perceptually matches if we inspect it at this level of patches. So I think that's kind of interesting with respect to trying to introduce a little bit of control from a visual perspective. Often when we see this kind of shapes, we might think of images that are similar from real world examples or from Google search and so on to be able to provide a bit of inspiration here. But we also have, from a sort of more scientific perspective, the opportunity to try to take the inverse perspective on this notion of learning priors and then doing an optimization. In fact, we can try to do this the other way around and leverage the power of optimization first before learning the priors. In particular, with neural fields, they can represent a very compact data structure for our optimization. So with like high dimensional data, like 3D shapes, and we have this very effective way of mapping a 3D shape and encoding its information into a relatively small coordinate field MLP here. So just the XYZ coordinates as input, and this is being encoded as an occupancy representation of the shape, optimized with binary cross entropy for values that are on the surface, and 0 values for those that are in empty space. And with that, we can actually very effectively reconstruct a single 3D shape instance, effectively sort of overfitting the weights of this MLP to encode all of the information of that shape, which can then just be decoded by sampling the MLP and running marching cubes. And here, despite the sort of high resolution nature of that data, especially in machine learning kind of popular representations of points and voxels and so on, our neural fields that we use are around 30,000 parameters. So it's a pretty compact kind of representation. And you can do the same thing for not just 3D, but actually 4D sequences. The main difference just being the extra time component in the input, but still being represented as an occupancy field over the time, and compressing this 4D sequence data into just the 30,000 parameters of the MLP. So that means that we have an opportunity to really interpret these small MLPs as weight vectors, just the weights and the biases of the optimized MLPs, both for the 3D data as well as for the 4D sequence data. We can just interpret them all as these optimized weight structures. So we want to then apply the generative model, not on the raw sort of high dimensional information of the 3D or 4D shape data, but directly onto the MLP weights that we use to optimize for the shapes. So we want to be able to produce a generative model that actually produces these MLP encodings of 3D or 4D shapes. So here you can see the visualization of just the optimized set of neural fields here. And because we're optimizing for every train instance individually, we can actually get a pretty high level of detail representing every individual object or shape sequence. So then once we apply this overfitting, we can use a diffusion model in order to learn this process of how to generate new MLP weight vectors. So the overfitting we've just seen, taking all of the trained 3D shapes and optimizing a coordinate field MLP to represent the shape. And that MLP can then be interpreted as just the raw vector of weights and biases of the MLP, and for every single train object. Then we can go ahead and try to model that noising process here on the weight vectors directly, right? So here we don't have a notion really of 3D shapes, but only their compressed weight vectors that represent the coordinate field MLPs. And this is being modeled with a transformer to predict the noising process here. And once trained, we can then sample new vectors of MLP weights that can just then be unflattened back into the MLP representation, on which we can then just run marching cubes to get out the new shapes as well. So this is a kind of dimension agnostic approach. We can easily apply it to both 3D and 4D data, not at the same time. That's not something that we've tried, but the 3D shapes and the 4D shapes can both be interpreted as the MLPs. And then we can model this generative model with diffusion directly on the corresponding weight vectors of each of them. So just to give a bit of visualization here, so we moved a little bit away from the intuitive control knobs. So here you see the weight space of the MLPs starting from Gaussian noise, and they're being denoised into something that now corresponds to a valid 3D shape. Here, of course, despite that they are actually corresponding to valid 3D shapes, it's not that we can easily make an intuitive sense of the actual MLP weight space that you see visualized on top. And so you can see this again in terms of the denoising process, we eventually get to something that looks a bit more structured, but it's a bit hard to say exactly what the control norms might be in this MLP weight space. On the other hand, what's kind of cool is that the diffusion is learning something about the structures of these MLPs that is actually shared across the train instances. And all that we're doing there to encourage this to happen is to provide the same initialization for the overfitting process for all of the train shapes before applying the diffusion. And so that allows us to then sample new shapes. Here, we have a bunch of airplanes in comparison to some state-of-the-art point-based diffusion methods, as well as a voxel-based baseline. And we can get from this neural field representation of just the MLP weights, maintain a pretty high resolution and fine level of detail on these objects, especially here, for instance, in the cars, we have a nice separation between the wheels and the car body. So we can also, of course, do this at the 40 sequence level. And here the compression matters a lot more because of the extra dimensionality here. So the voxel baseline is suffering pretty heavily from this high amount of memory and compute required to represent a deforming sequence, whereas we can actually just represent the compressed vector of the 40 sequence and still maintain the fidelity of the deforming shape here. So of course we can ask, does this actually generate new shapes that we're talking about? And to some degree, it is imagining new shapes. I think it's mostly a bit of interpolation between stuff that it's seen before. You can kind of see the way that chairs have been sort of pieced together here in terms of the generated shape, where the bottom part of that chair is kind of similar, but not quite the same here. And the top half of this particular chair looks a bit more like the chair back here. So we do learn in some sense to combine a bit together the part level information of train shapes, which is kind of interesting because we're actually operating in a somewhat unintuitive weight space of the MLPs. So that's basically a lot about how to potentially generate shapes and shape textures. I wanted to briefly talk about how we can potentially scale this to the scene level. And my take here is that we actually don't have enough high fidelity 3D scene data. So a few years ago, we did work on the ScanNet data set to collect a large scale setting of a bunch of 3D scene environments, but the geometry quality is relatively low. You see all these kind of artifacts and small objects have a lot of difficulty in being resolved. Here, we're actually taking a look now at collecting a much higher fidelity set of indoor 3D scene environments. And in fact, what that means is that we not only get a lot of finer scale detail of the objects, but also we can resolve much more cleanly small scale kind of objects here, not only in geometry, but also in color and appearance in terms of high fidelity color too. So the capture here is looking at high fidelity geometry, color, and then also a commodity level iPhone RGB stream so that we can get the different associations between more average person kind of use, where the average person can still afford an iPhone, but to something that many people have access to a device versus the higher end kind of geometry. In particular, we have a Faro laser scanner, a DSLR, and the iPhone. And so this is gonna, I think, produce a lot of interesting samples of high fidelity 3D data, not at the level of billions of images that we have now available for training, but a few critical examples of what high fidelity 3D scene data looks like so that we can potentially connect it with other sources of information. And so here you can see an example of the geometric reconstructions along with the blue camera frustums are train images from the DSLR image capture, the red ones, test images in order to test out novel views that are not in the distribution of train capture. So what I think we're looking at is trying to be able to provide that signal that can allow us to combine together now all this information about geometry, semantics, color, and appearance in order to be able to drive forward new generative models at the level of 3D scenes. So this is an ongoing effort, and I'm talking to you about this now slightly before it's publicly released, because we are currently at about 400 scenes. And I'm also hoping that if any of you have any spaces that you could potentially donate to this effort, that you let me know, because we want to be able to model a diversity of environments in these high fidelity scene captures. So just in terms of the research side, we're also looking at benchmarking novel view synthesis in a structured fashion, as well as semantic understanding. And just an example of the novel view synthesis in one of the environments from the DSLR. Of course, this is a little bit tuned so that you get better looking results, that you don't necessarily see some of the artifacts from more sort of test image kind of captures. But you can see really the difference in terms of the iPhone data, which has been captured more with the average user kind of setting. So all of the default camera video settings are there. We have motion blur, auto white balance, auto exposure, and this kind of stuff in the iPhone scenario in order to be able to understand how to bridge these together. So please do let me know if that's something that you're interested in terms of spaces. But with that, I would like to conclude and also thank the students and collaborators who've helped make all of this stuff happen.
Thank you very much, Angela. We have time for some Q&A. If you'd like to step forward to the microphones in the aisles, we can ask Angela questions, and then I will be reading questions out on Zoom. A question from the audience. Hello.
Yeah, thank you very much for the talk. I was wondering, how do you ensure multi-view consistency with the first project you were talking about? Because you have patch-based losses, I take it, which would be like very prone to like long-range inconsistencies of object textures, right?
Right, that's a good question. So mostly we're actually ensuring this based off of the learned manifold. We want to encourage multi-view consistency in all of the textures that we learn. In order to do that, because we're having this adversarial formulation from real images, we actually have a patch loss that samples patches from different views of generated textures and asks basically, do they come from the same shape? And then we also sample patches from the single view of the real images, and we ask, does that come from the same shape? So that encourages multi-view consistency. It doesn't guarantee it, but it generally does fix many of these issues of producing kind of the, one nice looking chair from the front and then different nice looking chair from the back. And once we have that embedded in the manifold, this sticks along as regularization during the patch-based optimization process for the one image query.
Okay, thank you very much.
Okay, we have a question on Zoom from Henry, who asks, in the hyperdiffusion work, how long does it take to generate?
So how long does it take to sample a new MLP wave vector? I'm not sure I have the exact timing on that one, but it's not too long in terms of order of like several seconds. The entire process is a little bit longer than you might hope because we have the two-stage process, but the first MLP overfitting step is actually very highly parallelizable.
And one from the room. Hi.
So I have a question about your.
Please come closer.
I have a question about your hyperdiffusion work. We know that with MLPs, we have these MLP parameters, we have a lot of symmetries, like we can permute the weights and permute the next layer weights, so on. So do you consider this in your diffusion process?
Yeah, that's a good point. We did try out some initial experiments there, but didn't really fully have time to explore, especially with permutations. I think it should be feasible, but it does become more challenging. So we're encouraging the MLPs to be a little bit similar to each other by starting with the same initialization for all of them. And when we apply the random permutation, it does disturb that similar-ish kind of structure. So it has a slightly more challenging time to then learn across completely random permutations. I think it should still be feasible, but that's mostly what we saw when we tried some first experiments there.
Okay, and one last question from Zoom. Kevin asks, could the hyperdiffusion approach be extended to generating scenes by predicting the weights of neural radiance fields?
That's also a good question. I mean, I think for shapes and NeRFs, this is feasible. For scenes, it might depend at the scale of the scenes. Certainly, you probably will require to have a larger set of weights to encode the very high fidelity 3D scenes for the effective novel view synthesis. And eventually, if that becomes too large, the diffusion process is going to be challenging simply due to the size of the weights. The other challenge, of course, is the amount of data that's available to train something like this at a general degree. And that is something that we are trying to address in terms of providing enough data to try.
Thank you very much, Angela. Let's thank Angela again for the exciting talk. Zoom people, can you hear us?
Yes, I can hear you.
Thanks. And Tim, would you like to
Okay,
speak
awesome.
share? Let's get that going.
I'll get started. All right. Yeah, I think we missed a couple minutes there on Zoom. But anyway, I want to thank the organizers for the invitation. I think it's an amazing program that they have put together, and I'd love to have been there in person. But unfortunately, I'm on holiday currently, so I'll be presenting remotely. I hope the technology works out. Do let me know on chat if it doesn't, and yeah, hopefully we can make something good out of it. Right, so I'll be talking about image and video generation with the still diffusion models. The content of this talk will encompass 6 different papers that we have recently put out. And I owe a great debt to all my great Google collaborators for this work, who you can see in the slide here. So I think it's a really very good time to have this this discussion and this workshop, because it's been an amazing year for generative modeling. At Google, we put out Imagine, our text-to-image model, and Imagine Video, our text-to-video model, both of which I was involved in. But we also put out Funaki and Party, another video model and another image model. And then, of course, outside of Google, there was DALL-E 2 and Stable Diffusion in the same year. So I think it was honestly the year of generative modeling. And in order to be able to appreciate this, I think it's nice to take a step back and see where we came from. So a lot of you just got started in this field. I actually got started in 2014. At that time, GANs just came out, and really they barely worked. Then we went on to autoregressive models. We came up with Pixel CNN and Pixel CNN++. And here you can actually see some of the samples that I produced at the time. At the time, I was working at OpenAI, and it was actually one of the first opportunities I had to present some of my work to Elon Musk. And I actually chose to show him these samples. Well, needless to say, he was not very impressed. But unfortunately, as a field, we progressed a lot since then. So there was an especially big step in 2019 when BigGAN for the first time was generating images that were truly persuasive, but still in a very constrained setting. So this is ImageNet, where you have basically a small number of categories that you can sample. And then really only as of last year are we able to generate arbitrary images from arbitrary text almost, and do so at a very high fidelity. So Imagine is our text-to-image model that uses diffusion to where you put in an input string and the output is a high-dimensional, high-resolution image, which actually is very detailed often, as you can see in this example. Here are some more examples. A transparent sculpture of a duck made out of glass. The sculpture is in front of a painting of a landscape. So we're asking quite a lot of the model in terms of compositionality here, and the model is able to do it quite well. The model can also go out of distribution, such as here, where we're asking for a photo of a rainbow-colored cow floating in the space above Earth, Milky Way in the background. Or here, where we're asking for a coffee cup with many holes. So depending on your perspective, this is actually a really great way of going out of distribution, or it shows that these models clearly don't know how physics works. I prefer the former perspective. It can also generate objects that we definitely don't want to exist in the real world, such as this toilet paper with real cactus spikes. Imagine really consists of contributions in 4 different pillars. So we have the data side, the model side, the sampler, and then we put it all together and we scale up to such a degree that we can actually get the most out of this. So for today, I will only really be touching upon 2 of these aspects, and that's classifier-free guidance on the algorithm side and the cascading super resolution model on the model side. At the basis of it all is diffusion models, which I won't go into detail about. You've already talked about them in the previous talk also. But it's this very nice setup for generative modeling, where we're smoothly interpolating between the clean image and a pure noise image for which we know the exact distribution. And then we use the learned model to interpolate between the 2. So Imagine is a cascaded pipeline where we start out with a frozen text encoder, in our case T5. We use it to embed the text prompt. Then we feed the embeddings and the initial noise distribution to the first stage of the model. We get out a low resolution generated image. Then we have a super resolution model where we feed the embeddings and the low dimensional generation into the super resolution model, and we get out a higher quality, higher resolution image. And then at the third stage, we put in the embeddings and the higher resolution image and get out our final product. And at each of these stages, we fill in a lot of the details. And actually, these embeddings are still very important. So even though you might not think it, there's actually a lot of detail in the image that captures information that is represented in the embeddings. One key ingredient to actually make this work that I thought was very non-trivial at the time is something called guidance. So what our diffusion model does is it maps intermediate noisy images to the clean image, which in practice we often do by parameterizing the model in terms of a prediction of the noise itself. So it's kind of like a residual prediction. We don't predict the clean image, but rather the difference between the clean image and the noisy image. Which, if you do the math, actually is the same thing as modeling the score of or the gradient of the log density of the image given the prompt, the noisy image given the prompt. A trick that the folks at OpenAI then came up with is to modify this noise prediction by adding in the gradient of a classifier model. So now what you're doing is you're not just saying move away from the noise and towards the clean image, but you're also saying move towards a noisy image that actually looks like it is very, very clearly classified as a dog in this case. And what that does is it actually produces images that are more typical of the prompt that you're asking for. And we typically find that this also improves the sample quality by a lot. We then took this trick and we modified it so that you no longer need the classifier. So rather than having an explicit classifier, we form an implicit classifier through Bayes' rule. So the probability of the text prompt Y given the noisy image X is proportional to the probability density of the noisy image given the text prompt divided by the unconditional density of the image. So we put in this implicit classifier. What you get is this difference in log density terms or score terms for the conditional and the unconditional case. In practice, we then again put in the model predictions. So that's the epsilon prediction, where for the unconditional case, we simply put in a 0 prompt. So during training, with about 10% probability, we drop out the actual text description of the image, and we just put in a 0 token. And then at test time, we evaluate both the prediction with the correct embedding and with the 0 token. And we scale in the direction of the correct embedding. We find that this trick improves sample quality by a lot. So as we increase the weight of this guidance procedure, we move from the bottom left of this graph to the top right, where on the x-axis you see clip score. So clip score is a measure for how well we're capturing the text embedding. And this also correlates quite well with what we tend to see as sample quality. And on the y-axis, we have the FID, which is more of a measure of how faithfully we're actually capturing the data distribution. So what happens initially is that both FID and clip score improve. And then as you have more and more guidance, the clip score still improves, but the FID gets worse. So it's a trade-off, really, between diversity and sample quality. And then in practice, you also need to have some thresholding in place for this to be stable. And we find that if you do this in a dynamic way, you get a better trade-off between the two. So this trick is also part of DALL-E 2 of stable diffusion of all of our video models, of most of the other video models in the literature. And it's it really seems to be the key that actually allowed us to get to GAN levels of images with diffusion models. So once we did this for images, our natural next question was to ask, can we also do the same for video? So that's what we looked at in the Imagine Video project. You see a little bit of an example here already with a teddy bear washing the dishes. It turns out we can just by using the exact same recipe that we used for Imagine, but applying it to video. So again, we have this cascade of different models. In this case, it's even deeper because the dimensionality of what we're generating is larger. We have not just the image, the frames, but we also have the time dimension. And we also go to quite high resolutions. So we actually ended up with this setup where we have 7 different diffusion models in our pipeline. So we again start out with a text embedding given by T5. And then we use the base model to give us a very low resolution video, both low resolution spatially, but also in time. So it's only 3 frames per second. And then we super resolve that in both time and space using temporal super resolution models and spatial super resolution models. So we do this 6 times and we end up with this high dimensional video that actually captures a lot of detail and is at high frame rate. So the video model itself is really, again, a simple adaptation of the 2D case. We simply take our 2D UNet, apply it to each frame in parallel, and then we have some additional layers in between that allow us to exchange information across frames. So the temporal aspect is only modeled by adding a couple of additional layers compared to the original Imagine model. And this also allows us to train jointly on images and video, which is very important because we actually have a lot more varied text and image data than we have for the video case. So here are some of the examples of what the model can do. So here we're asking for a bunch of autumn leaves falling on a calm lake to form the text Imagine Video. And I think this is a nice example of showing that the model is great at spelling, which most of these models are not. And also that it is able to actually do the animation from start to finish exactly in the time that we're sampling for, which is not something that is we're explicitly telling the model. But what guidance does is it forces all the content that we're asking for to actually complete within the span that we're sampling for. So guidance will actually then make the animation fit this 5-second video from start to finish, which ends up working quite nicely. So here's another example of that. Sprouts in the shape of text, imagine video coming out of a fairy tale book. It can also go out of distribution, such in this case where we're asking for a wooden figurine surfing on a surfboard in space. Or this happy elephant wearing a birthday hat walking under the sea. And here we're flying through an intense battle between pirate ships in a stormy ocean. So I like this example because it's both shows the potential of these models, where we're really moving towards like a scene of a movie. At the same time, it also shows what is still lacking. So the temporal coherence and dynamics are definitely not perfect yet, as you can see. Final example is this drone-like footage. There's a lot of drone footage in the data, and it also comes out quite nicely. So that was the big model, Imagine Video. We also evaluated parts of that model on smaller benchmarks from the literature, which we did in this video diffusion models paper. And turns out that it also works quite well in that setting. And so on small data, it's also quite competitive to the existing methods. So here we're looking at unconditional generation on the UCF 101 dataset, where at least at the time, not sure about what happened in the last half year, we were state of the art. The model can also be used for video prediction. So video prediction is a task where you're given 1 or 2 frames to start your video from, and then the task is to sample the remainder of the video. And the most well-known application of this is this robot pushing task, where you're predicting where this robot arm will move to. So we actually use this just by using an unconditional model. And at sampling time, we force it to be consistent with the first 2 frames or first one frame that we're given. So we're sampling the whole video, but we're forcing the first frame that we're sampling to be equal to the frame that we're given as input. And this actually turns out to be enough in order to have good video prediction quality also. So also here, we're getting very good results compared to what's been done before. The remaining question is then if this is to be used for content creation and be used in an interactive way in a nice product for the user, how do we make it practical? Because naive sampling of a video with this big model actually takes more than 10 minutes. And in practice, you actually want to experiment quite a lot with the text prompt that you're given, that you're giving in. And you want to try multiple things. You want to have feedback and see how you're doing. And 10 minutes is really too long for that. We believe generative models really need to be fast. So our solution to that is to actually distill the diffusion model into a model that's much faster to sample from. And it's faster than to sample because we're distilling it down to using just 4 to 8 sampling steps, which means that we can actually generate a 5-second video in less than 30 seconds, which is just right about where it starts becoming useful, I think. We proposed this method in a Nightclear paper last year, and we have extended it only recently with the CVPR paper that will be presented on Thursday. So do make sure to also attend that session if you're interested. We also have some open source codes that I think clearly shows the basic algorithm. So also a good reference. So what exactly do we distill then? Well, for these models, for diffusion models, we can sample in 2 ways. We have this SDE view, where the sample paths are these random lines on the top left here. And we have this ODE view, where the sample paths are actually deterministic and they're smooth lines, as you see on the top right. So it turns out that really the 2 views are almost the same. So on the bottom left, I've separated out the deterministic part in the stochastic differential equation, which is then the same thing as the deterministic ordinary differential equation on the bottom right. And it's really what's in this green box that represents a deterministic mapping between images along our sample path, and that's something we can distill. The remainder part can be seen as lunge event dynamics. So what that does is it does some sort of error correction, which we can actually add back in later, as we'll see later. So what progressive distillation then does is it takes a integrator of this ODE, a deterministic sampler like DDIM, for example, and it takes every subsequent 2 steps of the sampler, it distills it into 1 step, thereby halving the number of steps that you need in order to sample your output. You can repeat this multiple times, thereby halving the number of required sampling steps at each stage until you're at the number of steps that you're comfortable with. So then the student model at every stage becomes the teacher model in the next stage of distillation. So here's what the algorithm looks like. You start out with a teacher model. So this is a denoising model that you train in the usual way. You initialize the student as being equal to the teacher, so you just copy its parameters. Then in order to, we sample our data in the usual way. So we take actual data from the training distribution, add noise to it. But then what we do in order to get our training signal is that we do 2 steps of DDIM integration with the teacher model. So 2 steps of deterministic sampling. Then, given the result of the teacher model, we back out what the prediction would have needed to be if our student were actually to arrive at the same result, but using just 1 sampling step. So there always exists one particular distribution for which a 1-step student sampler will actually end up at the same place as the 2-step teacher, and it's given by this expression. So this we then plug into the loss. So this is what we denoise towards, and by doing so and by optimizing it, the student then becomes the same as the teacher, but taking less steps. So we do this until we're happy with the convergence of the students. Then the student becomes the teacher in the next step, and we halve the number of sampling steps again. So this is what the results look like. So on the y-axis, we have, again, FID. On the x-axis, we have the number of sampling steps. And we're comparing against an optimized deterministic baseline and an optimized stochastic baseline. So for the stochastic baseline, in this case, we optimize the variance of the noise that we're adding at every step. And we optimize that separately for each number of sampling steps. So it's really quite a tough baseline to beat. But what you see is that the distill model is much better when you go down to very few sampling steps. And we can, in practice, go down to 4 to 8 sampling steps to still have something that is almost indistinguishable from the original model, but much faster. So that was the original model that we proposed last year. This year, we're proposing this extension, which shows that this approach actually also works with classifier-free guidance. It works with stochastic sampling. It works with more sophisticated text-to-image models. So the models I showed you previously are still these more simple data sets. It works for image-to-image tasks, in painting, and also latent diffusion models. So the samples you see on this slide are all from Stable Diffusion. Right, so let me very briefly summarize what the extension to this algorithm does, and then hopefully we'll have some remaining time for questions. So in order to distill a guided model, what you need to do first is actually distill this 2-pass model, the 2-pass guided prediction, into a one-pass prediction. So what you do during training time is that you don't just sample this time and the time parameter in the data, but you also sample the guidance parameter from a particular range. And then your distillation target actually is the guided prediction, depending on W. And now the student model takes in W as an additional input. So it takes as input an embedding of the amount of guidance that you want to use, and it scales its prediction accordingly in a learned way. So the model actually learns to predict for a whole range of guidance parameters. And in the second step, what we then do is do progressive distillation in the standard way that I showed you previously. But again, also sampling this W parameter along the way. Another extension that we made is that we show that you cannot just use it for deterministic sampling, like we show at the top here, but you can also use it for stochastic sampling. The change, again, is actually quite minor. So what you do is you distill to use twice the step size. So the blue arrows are the deterministic sampling steps that we're taking. They're twice as long at the bottom of the slide compared to the top. But then we go backwards in time by adding noise in between. So by adding noise, we still retain some of this error correction that makes stochastic sampling work well in practice. And now we can also use that with the student model. So what we find is that both the deterministic setting and the stochastic setting work quite well. But if you go to very high guidance, then there's still some advantage to using stochastic sampling, as you can see in the result in the red box here, which has a better inception score compared to the deterministic case. And then we also show that it actually scales. So we can actually apply this to more sophisticated models and also to models with latent diffusion. So here you see some samples from our distilled stable diffusion model using just 2 denoising steps. And it seems to do quite well there also. So let me summarize and conclude the talk and then go to questions. So first of all, I think really this is a great moment to be in this field. Generative models are no longer just a science project. You can actually use them for serious content creation now, which of course is exactly what you're exploring today in the workshop. Diffusion is really the new dominant paradigm for generative modeling in this setup. It's stable, it's produces high quality results, and it's very flexible and allows you to do many amazing things. But we believe models need to be fast to be useful, and distillation is our proposal to make them fast enough to be useful. Thank you. Any questions? So I think we have 2 more minutes. I'm monitoring the chat on Zoom. So if anyone has any questions, please either speak up or put them in the chat.
Could you hear us? Sorry, could you hear us?
Yeah, I can hear you now. Thanks.
Yeah, sorry. Could you repeat the question?
Can you hear me as well?
Yeah, perfect. Yeah.
Okay, great. So I was wondering, given that you can distill this sampling process down to just a few steps, kind of naturally raises the question of why can't you train the diffusion model to do that in the first place? And it reminds me a bit of the work in like model compression, where people take, let's say, a large CNN, compress it down to a small one. And there the argument is that the over parameterization of the network means that you have the optimization landscape becomes easier. You have more local minima, which are equally as good. That reasoning doesn't quite seem to apply here because the student model that you're learning has the exact same number of parameters. I'm just wondering, like, how do I wrap my head around what's the intuition behind why this is difficult in this diffusion distillation case? Or if not, do you think it might be possible one day to train models that are this high quality, but you only need a few steps at training time?
Yeah, I think that's a great example, a great question. Let me try and answer it. I think my slides should still be visible, right? Right. So hopefully this is still visible. So the main difference when training a diffusion model and distilling the diffusion model is the target that we use for denoising. So in the original, when training the original model, what we denoise towards is the clean data point. But this is something that's ambiguous because for any noisy image that I give you, there's actually multiple plausible clean images that could have led to that noisy image. So what you do when you denoise towards the clean target is, in practice, you tend to predict kind of the average of all the plausible images that could have led there. So you, by definition, get something that's blurry and then needs to be cleaned up by more sampling steps. Whereas what we denoise towards in the distillation case is a deterministic target. It's a target that's given by running this deterministic sampler forward by 2 steps. So it's always gives you a unique target for any input. So you can have a very sharp prediction then, and actually losslessly just denoise the target, whereas that's just not impossible for the standard setup. So there's really a fundamental difference there.
Well, thanks. Any other question? Please go ahead.
Yeah, so thanks so much for the talk. On the vein of the distillation, I was wondering, can you take one of these few step trained models and then actually use it for more steps than it's trained on? Like, because it seems to, in some ways, be a more powerful model in that it can take that move in one step. But if you take this two-step model and say use it for 8, are there increased benefits to that versus just the vanilla, or not vanilla, but compressed 8-step model, if that makes sense?
Right, right. So I guess it would depend on how exactly you do the distillation. So the way we do the distillation is we only evaluate the model at particular discrete time steps. So if you distill down the model to use 4 sampling steps, typically it only then knows how to denoise at 4 discrete positions in time. So then actually loses the ability to take many more steps. What you can do, and what we do show in this this paper that will be presented on Thursday, is that you can basically move backwards in time by adding some noise. And so if you keep the number of sampling steps, the size of the sampling steps the same, and you add noise, then you move backwards in time, which means that you take more steps in total, and then you indeed do get a better result. So I guess the short answer is yes, you can do what you're saying, and the way to do it is by adding noise to the sampling process.
Oh, so that's it. So even though they're very good at taking that one big step, they don't actually kind of interpolate the ability to take smaller ones.
Right, right. The way we train now is you lose the ability to evaluate at any point in time.
May I ask one more, or keep one soon?
I need to ask a question from Zoom. Sorry about that. So one question from Zoom is the cascade structure of imaging video includes many diffusion models. So for the imaging video model, all the modules of imaging video need to be distilled. So how does that work for the video distillation?
Right, right. So they're not required to be distilled. So you could, in theory, distill one of these stages and not the others. Of course, what we care about in practice is the total runtime of all of the 7 stages combined. So then it does make sense to distill down all the models, which is what we did in practice. And yeah, what we did for that particular model is we distilled down to 8 steps per stage, for every stage. For the later stages that just do the super resolution, that's actually fairly simple to do. So you can actually go down lower if you want, but they already don't take that much compute. For the top stage, it's more difficult. So you need to train the distillation for longer. But that's also where most of the gain is had.
Thank you. So yeah, if you have more questions, feel free to contact him with email. I actually emailed him before he replied me very quickly. Anyway, let's thank Tim again, and thanks for your attention.
Thank you.
Yeah. Bye. Yeah.
Okay, so now we have our first poster session. Every poster is eligible to win the best poster prize. So we're looking forward to all of your efforts there. The posters are in the other building. They are in the West Exhibition Hall. Poster authors, your poster ID is on the webpage. Find the number that is next to your poster. That's where you shall put your poster. How do we get there? We go over into the other building, up the little stairs, and then there are escalators on your left that go down to where the posters are. So we will see you at the posters. After that, we will reconvene at 1:30 p.m., where we will kick off with a talk from Jiajiang Wu at Stanford. See you all soon. Sincere apologies for the delay. Let's kick off the second half of
the workshop. So lined up for you, we have 4 oral talks that were selected from the paper submissions. Then we have Jiajiang Wu from Stanford, who's going to be talking about representation learning. Xi Zhaosan from Microsoft, who is working in generation of an interesting area of visual design. Then we have a small break. Then we have Yuanjun Li from Google of Dream Booth fame. And then we have a special late breaking speaker, Xingang Pan, from this exciting new work, DragGAN, that is to appear at SIGGRAPH, but we get a special preview of it today. Following that, we have a special panel of 3 local Vancouver VFX and games industry experts, and they're going to give us their opinion on whether this whole generative AI thing is useful at all. So I'm very much looking forward to that. So of the submissions, we had 39, 27 were peer reviewed. Of those, 17 were accepted. This gave us a poster acceptance rate of 63% and an oral acceptance rate of 15%. 12 of those submissions were previously accepted to other works, other venues, and so these were not peer reviewed. We conducted an award selection process to find a best paper and a best paper runner-up. This was conducted by an external committee from the organizers that looked at each of the accepted papers and then decided upon the 2 winners. So, we are very pleased to announce the Best Paper Runner-Up Award goes to Zhongping Zhang, Jian Zheng, Jacob Fang, and Brian A. Plummer for the paper Text-to-Image Editing with Unsupervised Image Information Removal. And we'll hear from them in just a minute. Authors, are you in the audience? Would you like to come up? Okay, and then at the same time, the Best Paper Award goes to Naoki Matsunaga, Masato Ishii, Akio Hayakawa, Kenji Suzuki, and Takuya Narihira for fine-grained image editing by pixel-wise guidance using diffusion models. Congratulations to you too. Oh, good job. Naoki, are you here? Yeah, let's get that. Oh. Forward. The best paper and the best paper runner-up are awarded thanks to sponsorship from Google, NVIDIA, and Adobe. All right, so let's proceed with the oral presentations. There are 4. We're first to hear from Juyang Choi about custom edit, text-guided image editing with customized diffusion models.
Well, can everybody hear me?
Yes.
Oh. And hi, I'm Juyong Choi from Seoul National University. In this presentation, I will introduce our paper, Custom Edit, Text-Guided Image Editing with Customized Diffusion Model. This is joint work of Seoul National University and Naver AI Lab. Recent works on text-guided image editing using diffusion models like Stable Diffusion have shown intuitive and well-performing results. In our paper, we examined to what extent the text guidance can support precise editing instructions, especially those the Stable Diffusion may not know. Here we want to change the black cat riding a motorcycle into the cat from the reference. Naively captioning the reference and then editing fails to capture the precise appearance of the reference. In our paper, we show that customization of diffusion models is necessary before the editing. We propose a two-step approach that first customizes the model on given references, then edits images with textual prompts. Our key discovery is that customizing only language-relevant parameters improves the fidelity of text-guided image editing. After the customization, we generate edited images using attention map injection, which is proposed by the recent work called prompt-to-prompt. Our customization process largely follows custom diffusion, a recent work on fine-tuning diffusion models. The Stable Diffusion consists of self-attention, cross-attention, and convolution layers, and we only optimize keys and values of cross-attention layers and text token. While training only these parameters is comparable to training the entire model in the random image generation, we showed that it is crucial in image editing. And in the editing process, we first map the source image to the initial noise using null text inversion. Then we generated a new image with a target text prompt, including the customized text token. Preserve the structure of the source image. We regularize the denoising trajectory by injecting attention maps. The key challenge in image editing is balancing the source and reference similarities. We observed that a critical factor in controlling the trade-off is the injection of self-attention rather than the cross-attention. Our method transfers the reference's appearance to the source image with unprecedented fidelity while preserving the structure. Here we have a reference wood pot and a bottle of wine. Our custom edit turns this into a long restart wooden pot. Similarly, for another example, we have a cactus wearing sunglasses, and this turns into a wooden pot. Similarly, we have a reference tortoise plush and a sea turtle turning into the reference plush. And finally, we have a raccoon king turning into the tortoise plush, and see that it is wearing a hat with the texture of its own shell. As previously mentioned, training language-relevant parameters is crucial for image editing, like in random image generation. Here we compared to DreamBoost and textual inversion. We note that DreamBoost fails to generate the learned appearance, even though it trains the entire model. For quantitative comparison, we measure source and reference similarity with CLIP score. We vary the strengths of prompt-to-prompt to control the source and reference trade-off. Training only language-relevant parameters, indicated by a blue line, show a superior trade-off curve. Evaluation using STEdit also shows similar results. Also, custom edit shows various successful editing results. There are some failure cases. Custom edit sometimes edits undesired regions or fails to edit complex backgrounds. I think applying the custom edit on text-to-image models with better language encoders or extended controllability will be potential solutions. And this is end of our presentation. If you have any questions, feel free to contact us. For listening.
Thank you. Because we're running a little bit over, we're going to cut Q&A from the oral talks, unfortunately.
Okay.
Thanks, Juyong.
Hello, my name is Naoki Matsunaga from Sugi Group Corporation.
Okay. You can't see it on the screen. Really?
Sorry. Yeah. Hello, my name is Naoki Matsunaga. So today I'm going to present our research on controllable real image editing based on the provided semantic segmentation map. About motivation, considering a real-world application of image editing framework, it is important for creators that they can edit the every pixel level details as intended. So we focus on fine-grained image editing, which realize the desired edit according to the user-provided impression of a semantic segmentation map. In the literature of such fine-grained image editing, the previous scan-based methods fails to reconstruct the detailed appearance of input images, which is less observed in the training data. So, like pathsphere disappearing when we want to edit the eyes region. So we set our first and second goals to edit the visual contents, and the editing area should be created aligned with the user's intention while preserving the features outside that. Additionally, fast speed editing and low cost annotation are also required for real-world applications. Therefore, we propose a novel diffusion-based method to meet these requirements simultaneously. Here we show our editing framework. We show an example of editing hairstyle. At first, we prepared image X and estimate corresponding map Y using a label efficient segmentation model called pixel classifier of dataset DDPM. Then we manipulate it to the desired map Y edited by hand and specify ROI mask. It means an editing area. In the inference phase, inspired by blended diffusion, we divide the samples into editing area and preserving area. Then we obtain the first denoising sample XT0 using forward diffusion process. And in the editing area, we propose a pixel-wise guidance. As for the preserving area, we simply added a certain noise to the original image, then blend it with the editing area. We run this process iteratively at each time steps. For more details about pixel-wise guidance, at each time step T, we calculate a pixel-wise segmentation loss for the output of pixel classifier. This classifier is pre-trained in advance at each time steps. Then we obtain the gradient of this segmentation loss and guide the sampling process in the editing area. As for the preserving area, we add the noise. Finally, we combine these two areas and move to the next denoising steps. Since this guidance is conducted in a pixel-wise manner, it can satisfy the requirements. Here is a qualitative comparison with EditCAN. EditCAN is one of the baseline methods of segmentation-guided editing. We show an edited results based on the manipulation of semantic segmentation map according to the written text. These results demonstrate that EditCAN fails to reconstruct the detailed appearance of input images, like facial paintings and the person behind the cat. In contrast to that, our diffusion-based methods to edit the pixel wisely while preserving such features. Here is a quantitative comparison. Our goal is to edit the visual contents in editing area while preserving the features outside that. So we calculate reconstruction performance in preserving area and prediction accuracy in editing area. These results demonstrate that ours can outperform EditCAN in all metrics. Additionally, the effective combination of respacing techniques can achieve faster editing than EditCAN. Here is a conclusion. In this work, we propose a novel fine-grained image editing methods to meet the requirements for a real-world application of image editing framework. For more details, please visit the poster session or code and paper links. Thank you very much.
Okay, thank you, Naoki. Next up, we have Nick Huang. Nick, please could you screen share?
Can you guys hear me?
Yeah, we can hear you. Is everything good on the screen?
Yes.
Okay, thanks.
We are seeing
hi.
the not the full one. We are seeing the presenter view.
Oh, okay. Sorry. Excuse me. Is it fixed now?
It's like it looks like you're sharing a wrong screen. It's a presenter mode.
Oh, okay. Sorry for that. Please give me a second. Is it fixed now?
Yeah, it looks good.
Okay, cool. Hi, my name is Nick Huang, and I'm a master's student from Brown University. And today I'll be presenting text-free 3D-MM conditional face generation. So conditioning a pre-trained generative model is hard because the factors of variation in a data set are spuriously correlated. We see this even using state-of-the-art inversion techniques like high-fidelity gain inversion for HFGI by Wayne et al., where varying the head pose leads to strong artifacts and varying the facial expression leads to changes in identity and the appearance of glasses. And conditioning from scratch is also hard. Compared to StyleGAN 2, conditioning with existing face models like a 3D morphable model or 3MM here. InDisco face scan produces worse sample quality confirmed by a large FID gap. Deng and colleagues claim that this quality degradation is inevitable and is a tax we pay for controllability. We discovered that the quality tax is actually caused by poor conditioning of the generative model. We fixed this to achieve tax-free 3MM conditional face generation, where we obtain high-quality results even with large pose and expression variation. Correct conditioning achieves two things, consistency and disentanglement. Consistency induces a semantically consistent change in the generated sample. When generating a sample X using generator G and noise Z, if the condition in P is a smiley expression, then we want the generated face sample X to look smiley and not angry. InfoGAN formulates this problem as maximizing the mutual information between the condition P and the generated sample X. The mutual information can be directly optimized if the posterior P given X is tractable. For disentanglement, we want the condition to induce no change in any other attributes not controlled by the condition in the generated sample. If we change the condition P to be smiley, we should not suddenly change the identity of the person. Suppose we have conditions P1, P2 through Pn, where each controls the semantic attribute of the generated sample. We want the variation caused by one latent code Pi to be irrelevant to any other latent code Pj. So Pbos et al. Observed disentanglement through the second derivatives within the generator network. The first derivative describes the variation caused by one latent code, and if the second derivative is 0, then this variation is irrelevant to any other latent code. Let's apply this to human faces. The unconditional STLGAN2 takes noise Z and turns it into a sample X. Disco face scan conditions STLGAN on 3MM, which is a multilinear model from computer graphics over identity, expression, illumination, and pose. It concatenates the 3MM vector P and noise Z as input to the mapping network. An ad hoc objective named imitative loss is enforced between the sample X and the 3MM render to ensure consistency. But this struggles to correctly condition the generation because the domains are different, leading to worse results. Unlike disco face scan, our method feeds the 3M condition P as a separate branch to the synthesis network. This design is crucial to disentanglement. Then we directly optimize the mutual information as our consistency objective instead of relying on ad hoc losses. We know that consistency is achievable if the posterior is known. In our case, the posterior corresponds to 3-phase reconstruction. Any approach that can estimate 3MM parameters from an image makes it feasible to estimate the posterior. Disentanglement is more challenging. While it could be directly optimized via a Hessian penalty, this leads to an obvious drop in quality. Instead, we approximate the 0 second derivative conditions by the inductive bias of a carefully designed network architecture. The key insight is that the locality bias of a convolutional encoder leads to sparse first derivatives, and this approximates the disentanglement objective without any explicit penalization. And that's it. 3DMM is a powerful conditioner. We can see subtle expression changes, illumination, identity, and camera pose changes, and all still from a 2D generator. And our method closes the gap in FID while also maintaining disentangled control over 3MM parameters, effectively eliminating the quality tax. So thank you.
Thank you, Nick. I'm afraid we don't have time for questions. Nick, if you could unshare.
Okay.
Hi, everyone. My name is Skylar Zhang. I'm from Amazon Alexa AI. I'm an applied scientist. So today I'm going to present our work, text-to-image editing by image information removal. So first of all, let's have a look at our motivations. So text-guided image editing refers to the task given an image. People want to manipulate the content or the image by using the text description. So right now, most image editing methods, they're based on pre-trained image generation frameworks. They come from two different flows. The first method is based on optimization based method. For example, Imagic. So usually people fine-tune the pre-trained models on the input image. However, this kind of fine-tuning based model, they have the prolonging inference time problem. Also, they have overfitting problem. Another method is based on feed-forward transformation, such as ControlNet. They use structural guidance as an additional control. However, both those methods, they have the problem of preserving text-irrelevant content. So to solve this problem, we introduced the input image as an additional control to better preserve the text-irrelevant content. So here, because we introduced the original image as one of our input, so usually we will have, we will result in the identical mapping problem. So the reason is that right now, because of the lack of image text pairs, it's really difficult to train the model. So usually people train it using construction loss. So if the input has the original image, the model will try to reconstruct the input image. So, resulting in the identical mapping, meaning the input is, the output of the model is, very similar to the original input image. So we call this kind of problem as identical mapping. But for image editing, we don't want it to be like this. We want to edit the input image, right? So we propose the IIRNet, the image information removal module to solve this kind of identical mapping problem. So our model is composed of two parts: the conditional latent diffusion model and also the information removal model. So in our image information removal model, we erase the image information using two different operations, including color information removal and also textual information removal. So here shows how we do those kind of information removal. For color related information removal, we convert the RGB values to the gray values in the region of interest. In this way, we exclude the color information in the image. For texture related information removal, we actually add a random noise to the image condition, but in this way, we can destroy the texture related information in the original image. So besides those two operations, we also incorporate the structural guidance. Here in our model, we use the canny edge map, so serve as part of our model input. In this way, we can better capture the structural information. So here shows the experiment results. We evaluated our model on 3 different benchmark data sets, including the COP data set, the outdoor sea data set, as well as the COCO data set. So for COP and the outdoor seas, here we show the qualitative result compared with 3 baseline models, including ControlNet, Imagic, and TextureLive. So compared with the baseline model, we can see that using the information removal module as well as the original image as input, we're able to perfectly reserve the text irrelevant features of the original image. Meanwhile, we're able to generate images that align well with the text descriptions. For example, figure A, the first column, the baseline models, ControlNet and Imagic, they're able to know, the color of yellow and blue, but they fail to map the color to the right area or part of the bird. And for outdoor sea, let's take the second column as an example. So with our model, we're able to perfectly reserve preserve the original image information and successfully change the winter to summer. So we also evaluated the model on the COCO data set, which is more complex comparing with CURB and outdoor seas because it involves multiple objects. So here we show our qualitative results on different editing tasks. The first column shows our model's capability in object editing. The second row shows our model in C attribute editing. And the third row shows our model's capability in the texture editability. And the last row also shows that our model is able to preserve the original slated diffusion model's style editing capability. So instead of, besides qualitative results using, FID score or CLIP score, or we use LIPS evaluation metric, we also conducted user study to, further improve, evaluate our model's performance. So we randomly selected 30 COCO images, and we generated we generate images using the baseline models and also our model. And we asked 3 annotators to evaluate the generated image quality. So it's kind of like a multiple choice problem. So you can see here that our model wins the annotator's preference over the baseline models over 35%. So meanwhile, our model also is very fast during the inference time. So you can see that comparing with Imagic, it's almost 100 times faster. So we also did a few different ablation study here. So showing that for different image editing tasks, the noise level is different. So that's it for our presentation. So we have a poster session, so please welcome to visit our poster. Thank you.
first. Okay, I'm very glad to introduce Professor Jiajun Wu from Stanford University. Before joining Stanford, he was a visiting faculty at Google Research. He received his PhD from MIT. Professor Wu his work has been recognized by many prestigious awards from the community. For example, the ECM Doctoral Distinction Award, Honorable Mention, AAAI, ACM, SIG AI Distinction Award, and the MIT Thesis Award in Artificial Intelligence and Decision Making. Now, let's welcome Professor Wu.
Okay. I'll turn off video. Maybe this is better because I can watch this or something. Because yeah, stuff it's complicated. Okay. Yeah. Thanks, Jiajun, for the introduction. Very nice to be here. I'm Jiajun from Stanford. So today I'm going to talk about understanding the visual world through naturally supervised code. Visual world, we all understand what it is, right? We live in the world and we see all these, complicated structures and objects and scenes. And code is something that I feel like we are also very familiar with because we code using Python and stuff like that. Well, but here I want to show that, the word code or symbols in general can be interpreted more broadly in the sense that, what is a code or what is a symbol? What does that really mean? How that could be, possibly even incorporated into neural networks. In particular, I want to focus on this, what we call naturally supervised code. So this code, where are these code coming from, right? Possibly it can come from what I call natural supervision. So hopefully at the end of the talk, I'll be clear about, and you will be understand what I mean by natural supervision. Okay, so there's rich structure in the visual world. Is that proceeding? Okay. There's very rich structure in the visual world. If we live in scenes like this, all right, and we look at the pictures, then we see that it is just not just pixels, but there are a lot of structures such as there are planes. The corridor is made of, there's ceiling, there's ground, there are floors, and there's symmetry. There's reflectional symmetry, and there's repetition as well going on, right? The lights are repeating themselves, the windows are repeating themselves, the floors are repeating themselves. So if I ask you, what's going to be like if I turn around, you sort of expect those kind of repetition to continue. So now the question is it possible for us to leverage such kind of structural information, but together with the low-level pixels of object appearance for very smart scene understanding and editing? So here is a demo of what we want to achieve and actually what we have achieved, even though this is a while back. And we put this into Adobe Photoshop GUI, but the underlying algorithm is ours. What we did is first, we do interactive segmentation. That is standard, off the shelf. Anyone can do it, right? You just have a bounding box and you get a segment of objects, and then you compute a vanishing point. But then I can ask you, okay, how would it be like if I want to make the building taller? Just through one single step interaction, the users can drag it and then make the building taller. And at the same time, you can also make the building wider, for example. Right. So such kind of seemingly simple tasks actually requires your understanding at multiple levels of abstraction. Right. First, it requires you to understand at the lowest level the appearance of object. How does it look like, textures, and it should look kind of similar. At the middle level, you have to understand the 3D geometry, the surface novels of the object and the face of the building, and to which direction it is facing, so that it should still respect 3D geometry. And the highest level, there's repetition, there's structure, right? The windows are repeating themselves, the floors are repeating themselves. If I make the building taller, I expect such kind of repetition to continue. So let me show you how we're able to do this. So we're inspired by program synthesis work on what they did for visual data, where, for example, back in 2018, people have tried on these simple line drawings, and they're like, okay, this is a image line drawing with some kind of structure. What we can do is we first identify the entry-level primitives in this picture. In this case, that's lines and rectangles. So you can think about it as we're trying to vectorize the image, right? So we have this raw input image, which is like 250 by 250, which is really high dimensional. So it would be really hard to, for later program synthesis method to scale to such a high dimensional space. But if we vectorize it, right, think about it as we're turning this PNG file into a PDF file, right, or into a SVG file. Now okay, the scene is just a collection of entry-level primitives like lines and rectangles and their positions. And you can apply, a combination of learning and program synthesis methods to search for the program that explains such kind of lower dimensional space. Okay, now once you have that explanation or high-level structural representation, you can do things like extrapolation, make this pattern wider. This approach is kind of cute, but it has clear limitations as it assumes we have the library of object primitives on lines and rectangles, but how can we generalize to natural images, right? We don't live in a world that only has lines and rectangles. If I show you a picture like this, which is a bowl of milk with some kind of cereals, there are clearly some kind of patterns or structural representations in the image. But here, the entry-level primitives, if you think about it, you can say it's a cereal, but how to represent it, right? It has complex appearance. It's not just a single line. We were inspired by this long line of work in computer vision called, for example, internal learning or single image learning, especially by Mihaly Rani's group. They have been working on this for decades now, right? So the key observation here is if you just look at a single image, then realize there are multiple patches within a single image that look extremely similar to each other. And such kind of repetition can happen at the same scale as in these kind of red boxes, but it can also happen across different scales, right? There are green boxes. Right? Why do they exist such kind of repetition or similarity within a single image? That is fundamentally because, especially for the grasses, then that's kind of the same type of object, right? It's the same species. They're just different instances of the same object species. But so they of course just have to look similar. But because they live in 3D and we take pictures in 2D, so there's 3D to 2D perspective projection that objects that are closer to you, of course, appear to be larger. So that's why such kind of repetitions can happen, at the same scale, but also across different scales. So we have this important observation. How can we use that to identify these repeating objects? So people have tried to do that with deep learning in the sense that, okay, we can take these kind of pictures with these patterns or structures, we send it into a pre-trained neural network like ImageNet, pre-trained AlexNet, and then I can take activation maps and compute, how likely these activation maps are going to repeat themselves, or what is the self-correlation of these activation maps if I shift them by a certain number of horizontal pixels and vertical pixels, right? So if I have all these feature maps and move them, how likely are they to repeat themselves? And X and Y, the displacement that really maximizes such kind of correlation, self-correlation, is most likely to be the gap between these repeating objects. Okay, the way that they use, the diffusion neural networks is supposed to be, more robust to the noises in the input image or changes in textures and lightings and stuff like that. So we took a similar version of this idea, but we made some changes, which allows us to identify the centroids of these repeating objects. So in that sense, you can think about it as you have a natural image, but now you're trying to vectorize. You're trying to vectorize the natural image so you get a structural representation of what the objects are and where they are. So you can actually now have this kind of what we can call it neurosymbolic representations for these input image structures. And one thing that is not captured is what is the object, right? Now you know where the objects are, but you don't know what is an object because you no longer assume the world is made of lines and rectangles, but you want to understand, you want to model the specific appearance of object, but that can be taken care of by a neural network, right? So here this is how this can be applied. That is, if you have a picture with a missing patch and you want to do this kind of image in painting, then the structural representation allows you to tell, okay, where to look at. Right? If I want to in-paint a missing region, I would say, okay, there's a cross that is missing. I really want to, I can put in some random background. But if you ask me what is my intuition about what should be put there, I would say, yeah, there should be another cross there. Right? So these kind of structural representation, the high-level symbols tell you where to look at. Where how to do it is actually taken care of by this lower-level neural network, which takes all these reference patches and smartly blending and putting this missing region. Right. So if you look carefully, you realize, okay, this missing patch is not the same as any neighboring patches. So I'm not just trying to copy what is next to me, but I'm trying to really smartly learning to in-paint. But the structural knowledge tell me where to look at. And I can do other things like extrapolation. I can put in another row of the missing of the patches. And I know I can do image extrapolation, right, on these natural images. But also none of the natural images are perfectly aligned, right? So there's always some deviations from the centroids of the actual centroid of object to their inferred, where the positions are supposed to be. So you can identify the irregularities and you can magnify this kind of irregularities. Okay. So this is a nice example about how we can apply the structural implementation to a single image, a natural image. But here we have an important assumption, that is, this picture, you sort of assume you're always seeing it from top-down view, right? But that's not the case if you look at this corridor example, because here, clearly, the image has multiple planes. They're 3D. So how can we generalize this approach to images with multiple planes instead of just assuming there's a single plane image? It turned out to be quite straightforward. We can have, all we need to do is to set the camera parameters. And once you have the camera parameters, you need a smart way of identifying where the planes are, right? How can you partition the input image into different planes? And for every plane, you have to set, where's the position of surface normals, their poses for each plane. And once you have those, you can rectify each of the planes and you can apply what we know how to do before. You're reducing the problem to a single plane reasoning problem. Right, so here the challenge is, now I have to find a camera. I have to find a smart way of identifying where the planes are. The problem gets just harder and harder, right? Because now you go from, synthetic images to real images from single plane images to multi-plane images. And, here you just have, many more candidates about, okay, which could be the right way to go, right? Okay, how can I, here we're relying on some bottom-up visual cues like vanishing points and wireframes. Okay, but even with all the estimated, wireframes and vanishing points, then you realize there are still multiple possible explanations about what could have or how the image could be partitioned. If you're relying on a pre-trained model, like, okay, whatever segmentation model, then the model may have seen many different pictures, just like humans, and we know, okay, that is the floor, that is the ceiling. But here again, we're trying to learn everything just from a single image, right? So here we're just given this single picture. There's no prior knowledge about what a floor looks like. So how could a model understand, okay, which one is the correct partition? How can it tell candidate 2 is better than candidate 1 or 3? So the idea here is, we really have to think about why this structure exists in the first place. Why would such kind of, let's look at this corridor picture, right? Why would this corridor picture looks regular at all? Or why would such kind of regularity, repetition exist in the very first place? They exist in the very first place because there's human preference. But when human, during this fabrication process, during the construction process, when we're trying to build these buildings and corridors, we have this natural preference about things that are regular and structured. Therefore, we introduce, repetitions into the scene. And now you're trying to infer them. But here you're we're always being like, oh, let's go from bottom up. We estimate low-level visual cues, and we do like vanishing point, and then we estimate the plane partitions, and then we go to infer high-level programs. But sometimes you also want to think about a problem in the other way. That is, what makes a correct program, or what makes a correct plane partition, right? If the plane partition is correct, what does that lead to? Right? The fundamental reason that this structure exists is because there's human preference in certain kind of regularities. Therefore, if you're able to solve this low-level vision problem well, let's say plane partition, then the plane you have got after rectification, they should just really be very regular because that's how these are things supposed to be. So let's say I'm the model. Let me give you this. Let me just move forward with this concrete example, right? So here we have 3 candidates. Which one's correct? I don't know. But let's just assume they're all correct. And I can estimate their surface normals. I can rectify them using the estimated surface normals. And then I can do what I know how to do before, right? Below are the rectified image, and can infer the programs that try to explain these rectified programs, like rectified planes. And then you observe, right? Only with the correct plane partition, the rectified planes will look much more regular, and the program or the structural representation you infer will also be much simpler, and they will explain the rectified planes much better. Right? So if you infer incorrect plane partition, you put part of the ceiling into the wall, then the rectified pictures will look very irregular. It will be much harder for you to find any structural representation to explain them. And even if you find them, they're not going to be able to explain the image really well. So here, the key observation here is this seemingly totally disentangled problem of bottom-up visual processing, plane partition, and the top-down program synthesis. They're not really disentangled. They really should help each other, and what connects them is human preferences. Here, with this high-level knowledge of, okay, the correct plane partition, the correct visual perception should really lead to the high-level, the most simple programs. I can identify the correct plane partition, which is the second one. And once I have all these, I'll be able to do other things such as view synthesis, but in an extrapolation way, right? If I look to the top left in this corridor, what I'm going to see, I should expect another light to come in, right, while maintaining these kind of structures. And at the same time, if I look around, right, if I'm standing in the corridor, if I look around, if I turn to my back, what I'm expecting to see. Right. Of course, there are infinite possible explanations, but I have to pick one. I'll say, yeah, maybe I'll just try to produce an infinite corridor. There's no infinite corridor in the world, but if I have to pick one, that seems a reasonable assumption. But at the same time, I will expect all the lights, all the shadows, and it seems to really repeat and continue. Oh, okay. So I should say this is really joint work, a line of work done by two very fantastic PhD students. One is Xiang Mao at MIT, and the other is Yikai Li at Stanford. Okay, so what's next, right? So we've been talking about going from these synthetic data, sort of, contrived, to natural images, assuming there's a single plane, to more general, multi-plane images. So what are we going forward? In some sense, you can think about it as 2D, I would say single plane and sketch images as 2D images. Well, this multi-plane thing, it is a little less than 2.5D because it doesn't really have any detailed geometry or depth or surface normals. But it's sort of kind of, thinking about it as you're wrapping them so that you're putting together a surface that you see. So you're going from 2D to 2.5D. I would say a little less than 2.5D, but let me just call it 2.5D. Okay, so what's next? Of course, you want to go to 3D. Right, but there's a subtle difference, and that is we're switching from a viewer-centric scene, modeling perspective to an object-centric object modeling perspective. In particular, right, just like buildings, right, man-made artifacts like the chairs you're sitting on, but they often have this very abstract and program-like structure, which seems a perfect candidate for these kind of structured representation. Right, exactly because when we made them, there are cost efficiency concerns, there are pragmatic concerns that things have to be stable, right? It has to be cheaper to make. Now we introduce a lot of preferences about the repetitions and the lags of the chairs, for example, as well as the regularities on the parts of the objects. So we have done some work inspired a lot by the classic work in computer graphics, but we realize it or we modelize it with the context of the neural networks, where we take a shape that we can use a neural program generator to infer the programs of the shapes. And because there are not that many annotations for the program of the shapes, we also have a neural program executor. So at high level, you can think about it as an encoder decoder, but we try to use the program as intermediate representations. But because the encoder and decoder are both neural networks, they're end-to-end differentiable. But more recently, we have also extended the work that we try to draw the same analogy as I said earlier. That is, if in the 2D, there's no reason to assume the world is made of lines and rectangles. In 3D, there seems no reason to assume, the program for the shapes has to be made of, geometric primitives like cylinders or cuboids, right? Instead, what is really shared or what is really the regularity or what human introduced into this shape during the fabrication process is things like high-level structures like symmetry. The thing has to be reflectional symmetric. Or repetition. The legs of the chairs has to be identical. But the specific geometry, what does the leg exactly look like? What is the specific, the curvature or the fine level decorations on the legs? These are things that are not necessarily symbolic, right? They can be, very, I would say, very detailed and carries all the information, but which is not easily approximated with just simple geometric primitives like cylinders or cuboids. So we want to, again, just like what we did for natural images, you want to have this kind of high-level structures like repetitions or for loops for the notion of, okay, the parts are reflectively symmetric. The parts are repeating themselves. But the specific geometry of the parts, just like the specific appearance of the serials, can be represented by neural networks. And of course, here we use this very popular, these neural implicit representations to represent object parts, the geometry of object parts. So what you can do is you can see that we're able to reconstruct the shapes like the airplanes and charts and tables with very fine details, but the parts that with the same color means they're represented by the same neural implicit networks, right? So you have this high-level program structure to guide. I'll say the planes, planes, the wings of the planes, the engines of the planes, they have to be the same, right? If a plane has, two different wings, I probably don't want to sit on it, right? So it has to be the same. But then the specific geometry of the wings, they can actually be represented by a neural network. And here in this kind of program or neural symbolic representations, I would say, there's guarantee that the parts are actually the same just because they're represented by the same neural networks. And these kind of high level structure are sort of suggesting, okay, which neural network, which part you should look at, right? For the plane, for the wings and for the engines and for the arms as well. Okay, I think I have 10 minutes or something, right? Oh, okay. I thought I have 30 minutes, right? Yeah, that's what I thought. I prepared the talk at 30 minutes, and I know we're 20 minutes late, so I assume we have 10 minutes left. Okay, I'll try to wrap up soon. So let me talk about this most important problem now. That is, we have been spending all the time talking about how we are able to get a structured representations for visual data, right? For 2D data, for 3D data. But why would these structures exist in the first place, right? Again, a lot of it has to be, all the preferences are from humans, right? So the program structure, they originates from human preferences in the fabrication process. So if we look at the picture of this vase example, then we understand, the picture looks the way it is because there are underlying intrinsic images, right? There's surface normals, which represent the geometry of the objects. There's the albedo, which represents like the texture of the objects. There's material, which is the reflectance of the objects, right? These are kind of different parts of intrinsic images that really got put together and produced the image the way it is. And a large part of computer vision is trying to just do inverse, you can think about it as inverse graphics, try to infer these intrinsic images from the input image. But among these intrinsic images, which part of it is more regular than others, right? What about shape? Right? If we look at this vase, then we realize, okay, the shape of the vase is actually, I would say, perfectly regular. That's fundamentally because when I'm trying to make it, I want to make this shape really, really rotational symmetric, right? So I have this kind of explicit structure that I try to introduce in the intrinsic image. And the same for material as well, because I understand, right? The thing is made of, it's homogeneous. It has the same material everywhere. Every point on the vase is reflecting light in the same way, right? So that's what we mean by, have this kind of explicit regularities or code that you can build into these two intrinsic images. And what about albedo? Albedo is kind of, looking similar to me everywhere, but it is not like every pixel on this albedo map have the same color. Right, so it has this kind of perceptual regularity, which I thought is much more implicit. It's not as explicit, but does have this kind of regularity built in. And lighting is often very complex, so we just assume it's not regular. So you can see that the problem of intrinsic image decomposition from input RGB image is really under constraint. That's why it's so hard. But now we have some subtle signals, right? This regularity or the asymmetries within these kind of structures, right? Some are more regular than others. So is it possible for us to leverage these kind of very subtle structure or biases, get a very minimal, prior, but allow us to do a lot in inferring a lot of these intrinsic images in image understanding and decomposition. So with my postdoc now, but back then he is a student at PhD student at VGG, Ilya Wu, what we did is, what we try to explore is we just want to leverage this kind of structure for image de-rendering, inferring these intrinsic images from the input image, and so that you can synthesize images in novel views. But because we're also modeling the materials of objects, right, you can also rely the objects, right? Going from a single image, you can see it from different views, you can rely them. So how are we able to do it, right? So very quickly, we were able to enforce these explicit regularities in the shape by parameterizing the object with a solid revolution representation, right? Because we know it is rotational symmetric, you can parameterize it with the low dimensional representation for the shapes. You can re-render the silhouette and compare it with the bound truths. Again, we want to do all this without supervision, so this is totally unsupervised. That's why the problem is hard. And once you have the shape, you can unwrap the image so that you get the surface normal maps and the texture maps. And once you have the surface normal and texture maps, you can do the standard image decomposition thing. You can get the lighting representations, material representations, diffuse albedos. But here, we're parameterizing the material with, using the same material parameterization for every pixel, every point on this texture and normal maps, right? This means, every point on this object have to reflect the light in the same way. So then you can do the standard, image re-rendering thing, just putting back to the standard image re-rendering pipeline, and then compare the reconstructed picture with the input image. So that's your second loss, Right? You can see that here we're sort of enforcing this regularity or explicit regularities in object geometry and material, but just by parameterizing their representation slightly differently. Right? So this is kind of a subtle way, but very important way of introducing these biases or code into neural networks. But it is just different ways of parameterization, different inductive biases. And there's nothing wrong with end-to-end training. It's still end-to-end differentiable. Finally, for albedo, we know it's kind of implicit regular. So how can I enforce it? We enforce it in two ways. The first is because it's kind of similar everywhere, although it's not like every pixel has the same color. I can compute a mean albedo, reconstruct the shape with that mean albedo, and the reconstructed image should look similar to the input. Yeah. There's a second way that is more important and I think most interesting in enforcing this implicit regularity is if these albedo maps or patches on the albedo maps are kind of similar to humans, they really look similar to humans, then it should also look similar to machines, right? So if I have all these, patches on these albedo maps, and then no matter whether they're coming from a highly specular region, that's the hardest part in intrinsic image decomposition, because a region that is highly specular, overexposed, really gives you very little information about underlying true color of the object. How can you go from this white pixel to infer the underlying color is actually yellow, for example, right? But now I have this important assumption or observation that is because the albedo maps is implicitly regular. So every patches on this albedo map, no matter whether they're coming from a highly specular region or non-specular region, they should look similar to humans and should also look similar to machines. So this is how we enforce it using this self-supervised albedo discriminator, which we name it. So specifically, you can take patches from this propagated albedo maps, and they may have different specularities, but you can send them into a discriminator, and the discriminator should not be able to tell whether the patch is coming from a specular or non-specular region. Right? This way, you smartly but implicitly enforces the regularities in albedo maps. Okay, so this put together the entire system. And here are some results on testing on natural images. During training, we train a collection of images of vases without supervision. During testing, given a single image, we're able to infer the albedos, normals, diffuse specular components, and materials in environment maps. And this allows you to go in from a single image so that you can virtualize it. You can see objects from different views. And you can rely them. And here's results on the different data sets. Oops. Okay, James is not happy. So let me just wrap up using 1 minute about finally how we're able to really, and again, I said a few times, right? Going from 2D pictures, you don't want to assume the world is made of lines and rectangles. In 3D, you don't want to assume, the shapes are made of cuboids or cylinders. But here, the material is general, but the geometry still assume it's a solid revolution representation, right? How can we generalize to natural objects, right? Without such kind of assumption, the world is not made of objects that are all rotational symmetric. Right. So if we look at more natural objects, like this bouquet of roses, which is presented at this year's CVPR, so you're welcome to look at it, even if I don't have much time to talk about it. The reason that these roses all look similar, right? It's not like they have this same rotational symmetric representation. It is really, as I said earlier, fundamentally because they belong to the same object species. There's the same object category. There's a reason that we call them roses, right? We name them because they all share what really makes them a rose. That is the intrinsic distribution of their intrinsics. So if we look at these multiple instances of roses, then they're just really multiple instances of the same object instances from the same object category. And therefore they have to share their underlying object intrinsics, what really make them the rose. That is, they have a shared distribution of object geometry, have a shared distribution of object texture and material, right? So what is really shared is not the rotational symmetric representation, but is the shared underlying geometric distribution. The distribution of object intrinsics including geometry, texture, and material. You can leverage that into our system by learning such kind of generative distribution and put them together with everything we talked about before, like extrinsic lighting representations and poses, and then making sure the generative distribution really approximates the examples you have seen from a single image, just a single image of 20 roses, which is approximate that distribution. That even this very simple framework allows you to approximate and learn very good distribution of object intrinsics for the same object categories like roses, just from a single image, which allows you to do all the things you do before, you can do before. Novel view synthesis, as in the line at the bottom, relighting, as in the second to bottom row. And now you have a generative distribution of object categories. Therefore, you can synthesize between roses of different geometries, right? So in the middle row, you can see that you can vary the latency. You can sample different roses of different object shapes, and then you can vary their poses, see them in different views, and relight them. This is also by Ilya, but also by my PhD student, Winter. Okay, some more results about going from a single image to learn this object distribution, so that you can synthesize their geometry and vary their lighting and textures. So we talk about this is 3D, and don't have time at all is to talk about the structures in time and human motions, which is another interesting topic. So to summarize, right, all these things here I talk about is, we have this neural network for recognition, but then you have some kind of structured representation for generalization or code for generalization. And people always feel like code is not good, right, because it's not general. But I would say, you have to interpret the code in a very broad way, right? So it's not just for loops. Sometimes you need for loops, but in most cases, these code can be just different type of inductive biases that you may need into your learning systems, so that the whole system can still be just a neural network. It's end-to-end trainable, but now you just put in different inductive biases that are really, actually makes it generalize better. But then the question is, where are the code coming from, right? How can we really define the symbols? Because there are so many options. So that's what I mean by natural supervision, in the sense that you have to look at what is the most fundamental and universal in the world. And in most importantly, I would say there are just two types of natural supervision. One is nature, as we see in the rose example, right? It is there's evolution. If you believe in evolution, there's specific object categories, and that's why they have to share the same intrinsic distributions. And there's perspective projection, how 3D world is projecting to 2D world geometry. But these are the most fundamental things, or naturally supervised code that we can leverage. And the second is humans. As we have seen in many examples, there are just different inductive biases that humans put into this fabrication process, which we should leverage for these smart understanding systems. And we can extend to more general scenes, develop better methods for more efficient inference algorithms, possibly connecting them from passive perception to interactive manipulation, and have fundamental connections to visual perception, to cognitive understanding, and to language description as well, which is another source of important natural supervision. Thank you.
Yeah, wonderful talk. Due to the interest of time, we don't have time for question, but please find Professor Wu and ask your question offline. So as you know, our workshop feature a rich portfolio of research topic on content creation. We have seen a lot of wonderful talk on creation of image, video, 3D. And next session will be a little bit different, which is about graphic design. So our speaker, Dr. Shizhao Sun, is a senior researcher at Microsoft. Her research mainly focuses on facilitating and automating the graphic design by artificial intelligence, which includes, for example, layout generation, visual asset generation, and design understanding. Yet without further ado, please join me in welcoming our speaker.
Okay, thanks you for the introduction. My topic here today is graphic layout generation. So what is graphic layout? It is the arrangement of visual elements. Taking this mobile UI graphic design as example.
There's no voice?
Can you hear
we
me
can
now?
see the slide, but we don't hear any voice.
We can hear from Zoom.
Oh, okay.
It might be on the room issue in the workshop. Do you hear anything, Lou?
Can you hear me now? Hi, hello.
James, Lou, do you hear anything?
Can you hear me?
I can hear Giselle, but oh yeah. Okay.
Okay.
Looks fine.
Okay.
Sorry, everyone, we
So-
can't hear the Zoom person right now.
So can you hear me now?
I do.
Okay. So when we see graphic layout, it means a set of elements, and each element is represented by 5 attributes, including element types like image, text button, and also the top left coordinate, width, and height. Here are more examples for graphic layout. For example, the web banner, the slide, and the document. It is a very new topic to automatically generate layout, but it grows rapidly in recent years. There are several hot topics for this area. For example, how to capture layout characteristics to improve the performance, and how to model diverse user requirements to improve user experience, and how to unify different tasks. In this work, I want to introduce 2 work about capturing layout characteristics. One work that takes textual description as the medium to control the layout generation. And I will also introduce our idea about how to unify so much conditional generation tasks. So let's go to the first work. One characteristics for layout is it is hierarchical. It contains several regions, and each region contains several elements, and each region appears like a simple layout, which only contains a part of elements from the whole layout. To capture such characteristics, we propose to decompose the decoding process. Our basic architecture is a VAE, which means it will first encode the layout into a latent variable Z. Then we introduce region decoder to predict the rough appearance of layout. And we further introduce element decoder to generate detailed element placement. In this way, a complex layout generation problem can be decomposed to several simple layout generation problem, and the predicted region can be regarded as a global context for the generation of elements. To better learn the regions, we leverage pseudo region segmentation as a supervision signal. Specifically, we segment the layout by green lines to get pseudo regions. We scan the layout by horizontal or vertical lines to get several parts. And for each part, we again segment by green lines until we cannot segment it again. After that, we will get a hierarchy tree. We take one layer in the hierarchy tree as our pseudo supervision signal. So the overall loss function for our approach is contains the reconstruction error for elements, reconstruction error for regions, and also the KL divergence. Here are some examples for the predicted regions and predicted layouts. We can observe that predicted regions can roughly depict the appearance of the layouts. And we also compare the performance of our approach and the baselines under different number of elements. And we can see the performance gap between our approach and baselines increase when the number of elements increase, which indicates that the advantage of our approach lies into handling very complex layout. So in the next work, let's move from unconditional generation to conditional generation and focus on how to unify this conditional generation tasks. So what is conditional generation? It aims at generating the position and the size of each element based on the user constraints. For example, in refinement, we take a bad layout as input and generate a good layout. For completion, we take a part of layout as input and generate the remaining layout. And also, we can take element types, size, and relationships as input, and then generate the whole layout. There are some meaningful attempts in existing works. A main characteristic of them is that they usually propose a specific method to handle each task without considering whether it can be applied to other tasks. That is, there is no sufficient flexibility in current approach. And another observation is when this method wants to make the layouts more conforming to the user constraints, the quality are usually damaged a little or largely. So in other words, there is no good controllability. In our work, we want to achieve both flexibility and controllability. So how do we achieve it? First, we propose a constraint serialization strategy to represent different constraints by a unified sequence format. Here we choose sequence format because it has been demonstrated to be very successful on many NLP and CV tasks. And sequence format is very inclusive. It can represent any structured user requirements and also unstructured user requirements. Then we leverage transformer encoder decoder to generate layout sequence from the constraint sequence. After that, we introduce decoding space restriction to prove the infeasible options in the predict distribution. So how do we serialize constraints? Here are 2 points. The first is how to represent one constraint. Here we define a set of vocabulary and then concatenate the tokens from this vocabulary. Take the generation condition on relationship as an example. The vocabulary could be one vocabulary for element types and another vocabulary for relative relationships like top, bottom, right, and left. And then we use tokens from this vocabulary like text top, text one, top, text two to represent one constraint. Another question is how to combine those constraints. Our strategy is to concatenate sequence of different constraints by a fixed order. For example, we can first concatenate the constraints of element types and then concatenate constraints for element relationships. And for decoding space restriction, first, the decoder predicts distribution at each step. Then we introduce 2 pruning strategy. The first one is to prune the infeasible values that violate constraints. And another one is to prune the values with very low probability. When all the values are pruned, we trigger the backtracking mechanism, which rolls back the decoding process and restarts the prediction. We conduct several experiments on all the typical layout generation tasks and observe that our approach can outperform task-specific approach. We have introduced some conditional generation tasks with very simple and explicit constraints like element types, element relationships. In this work, I want to introduce how to use text as a medium to control the layout generation. The reason is that text is a more friendly way. We know we may not have design knowledge, but we all can express our needs by text. So here is an example for text to layout. The user may see, I want to show several pieces of news each of these has a title and a brief summary. There should be a heading at the top. Then the model will generate the layout in the right side. It is actually a very challenging task. First, there are implicit constraints. For example, the title, brief summary, and the heading here refers to the text box in a layout. And also there are combined constraints. In this simple case, there are type constraints like title and summary, and also the position constraint like at the top, and also the hierarchy constraint like there are several pieces of news, each of them contains several elements. And also there are incomplete constraints. For example, the image is not specified by the user in this case, but we know as a piece of news, it's better to have an image here. But there are several opportunities for this task, which makes we believe it is possible. First, by taking advantage of large language model, implicit constraints could be transformed to explicit constraints, for example, from title summary to the text box. And as we have introduced, explicit constraints are well studied by existing work. Furthermore, although we do not have pairwise data with text and layout as a training supervision signal, the graphic designs and their layout are actually ubiquitous and easy to get. So with such observation, we propose a method to which introduce intermediate implementation to decouple the problem. Here is more details. When we introduce intermediate implementation, we will have two stages. The first stage is the parse stage, which translates text description to intermediate implementation. And the second stage is the place stage, which translates the intermediate implementation to a layout by using unlabeled data and labeled data. So for the parse stage, the critical problem is how to design intermediate implementation. Here we follow two design principles. The first one is expressiveness, which means it could be able to express diverse user constraints. Another one is formalism, which means it should be friendly to existing NLP technologies. Here we formulate it like a program. Then the task will be close to a semantic parsing problem, which has been well studied by NLP domain. For place stage, we adopt sequence-to-sequence model from Layout Former++ by more techniques on handling the characteristics of text-to-layout. The first one is how to handle combined constraints. We serialize each constraint and concatenate them in a certain order. Another one is how to handle incomplete constraints. We introduce a categorical attribute in the layout sequence to indicate whether element is given by users or auto-completed. But to train such place stage, we need labeled data with intermediate implementation as input and a layout as output. But such pairwise data is very expensive. On the other hand, unlabeled layout contains much patterns. So we decided to exploit unlabeled data. There are two steps. The first step is to pre-train the model by the synthetic data, where the intermediate implementation is automatically synthesized from layout. Another step is fine-tuning step, where we use labeled data to mitigate the distribution gap introduced by synthetic data. The common distribution gap contains whether an element should be auto-completed and when user says there is a small element, how small this element should be. We adopt several baselines from signal generation as this is the first work for graphic layout generation from.
The Zoom speaker got cut off as well.
We lost audio from the.
It dropped the big ones.
Hang on Zoom. No, nothing changed.
I think.
Oh, we didn't. Okay.
No. Okay, everybody. Oh,
There it is. We're back. We were back and now we're going again. Not anything for you.
PA's on.
Okay, so it's something.
okay. It seems like we have lost the Zoom connection at this.
Stay on with me for a second. Sorry. Yeah. Keep going. Sorry.
Okay. At this point, I think it is appropriate that we break for the people in the room. So let's take a 10-minute break and then we'll come back for the next session. I'm very sorry about this, everybody. I know we have a few hiccups, but hopefully we'll get things sorted by the next session. So we'll start again in 10 minutes. Thank you, everybody.
Right. I think.
I have no idea.
Okay. Okay. Hello, everyone. Let's resume our session. It's my great pleasure to introduce my colleague Yuan Zhen. And for me, I think Yuan Zhen is a legend. So after she got his PhD from MIT with Ted Edelson, she started her own startup. which was successfully acquired by another company. And then later she joined Google and doing both research and product. And today I think she will talk about the many interesting work she did at Google recently.
Thanks, Deting. Hello, I'm Yuanzhen from Google Research. So today I will be talking about a few of our recent projects, including Dream Booth 3D, Style Drop, and Muse. So these are projects that were done with many amazing colleagues, and a few of them are in this room today. So first I'll talk about Dream Booth. Nathaniel, our first author, will also be talking about this work on Thursday afternoon in the awards candidate talk session. So please do attend. So the background of this work is last year when the Imagine diffusion model that Tim covered this morning came out, we were just amazed by what the model could do, the beautiful images that the model could generate. But we did feel that there was one pinpoint, which was how can you generate images of specific things? So not images of a generic dog, but images of your dog. How can we make this happen? So, and also we want to generate images of a specific subject like your dog in all the new places and new settings that you can steer and create with text prompts. So that's why we did Dream Booth. So you can, the idea is that you can give a few images as input, typically 3 to 6 images, to tell the pre-trained text-to-image model what the subject looks like. And then we fine-tune the model and generate novel images featuring your subject. So these are some example results. On the left are the input images. On the right are the output images. So the images I'm showing here are generated with Dream Booth and Imagine, although our colleagues and also the open source community also later adapted the method to work on stable diffusion and also masked transformer models such as Muse that I'll also cover later. So here are more results. So in this example, on the left are input images featuring a specific pair of pink sunglasses. So given these images as input, we can now generate this pair of sunglasses in different settings. For example, worn by a bear on top of snow and also with Eiffel Tower in the background. So if we think about this problem, there are 2 objectives that we want to fulfill, we want to achieve. So first, it needs to have fidelity, have high fidelity to our subject. It needs to look like your dog, your product, or you. Second is that it needs to be able to generalize to really brand new contexts and brand new environments. So you might think that I could come up with a very highly detailed text prompt to describe my subject, but that often turns out to be very, very challenging. So how do we do this? So the idea is actually quite intuitive. So you want to insert knowledge about this specific subject into the text-to-image model. So we use a unique rare identifier, in this case denoted as V, and fine-tune the model to associate the input images of this specific dog, in this case, with this rare identifier. So we also want to take advantage of the model's existing knowledge, because the model has seen many, many images of many, many dogs. So it knows a dog very well. So we also want to leverage that. So in order to do that, we also use a class word, in this case, dog, as the text prompt to associate with the input images. So in this case, we use a V dog, V standing for a rare, unique identifier. And then we fine-tune the model. So while we do this, we also don't want to destroy the knowledge that the model has already learned. So in this paper, we used the prior preservation loss. So we basically also generated images of the class without the unique identifier, without associating with the specific subject. And then we also wanted the model to still be able to generate those other dogs. I do want to mention that after we released this paper last year, there has been many newer methods. So for example, custom diffusion that came out of Junyan's group, and also LoRa that was a method initially used for fine-tuning large language models, but also used later adapted by the open source community to use for this purpose that do have very nice regularization. So with those methods, you may lose a little bit of fidelity, but you don't need the prior preservation loss to regularize. So these are more results. So again, on the left are the input images of a specific backpack. In this case, it has a few stickers. And if you look at the output images on the right, you can see that the stickers are fairly well preserved. It's not perfect, but the results are quite remarkable. And this is another example. This is a vase, and now you can generate the vase in different settings, including being immersed in the ocean. This is another example of a teapot. So in this one, there's one example here, that's the transparent teapot holding milk. So it preserved the shape of the teapot, but it changed the material, which is quite remarkable. But if you look closely, you can see that it's not perfect. You can see that on the image, in the image on the right, you can see the teapot's handle and the spout are not quite right. So it's not perfect. The detail preservation is not perfect, but still most of the results are very, very good. These are just more results of a very specific dog being featured in different environments, and also of a specific cat being rendered in different viewpoints, and a car being rendered in different colors, and also a dog being blended with other animals. But you can see that it still captured the essence of the dog. It still looked like the result images still look like the Chow Chow dog, even when it's changed into another different animal. Here is a specific dog in different expressions. So that is Dream Booth. And then the next work that I'm going to talk about, Dream Booth 3D, is can we do this for 3D? So this work was led by Amit Raj and Varun Jampani and others. So the idea is also very similar. So given a few images as input, again, three images, 6 images, can you generate 3D? Can you render the object or the subject in 3D? So the two pillars that we drew inspiration from, one is the subject-driven image generation, including Dream Booth that I just talked about, and also including a few concurrent works, including textual inversion, custom diffusion, etc. And another pillar that we draw inspiration from is the text to 3D work that Ben covered this morning. So for example, Dream Fusion. So we want to say that, can we now also generate the 3D of not a generic dog, but your dog, not a generic product, but your products. So you might ask, can we just naively combine Dream Booth and Dream Fusion? So we tried that. So you have a Dream Booth fine-tuned diffusion model, and then you use that model to provide the SDS loss to Dream Fusion. But the results were not very good. You can see the result on the right. The dog doesn't quite look like a 3D dog. So our hypothesis is that in the Dream Booth step, it overfit to the input examples, and it lost some ability to generalize to different viewpoints. So we proposed this iterative method. So starting from the input images, we don't go all the way. We do a partial Dream Booth. We fine tune the model just a little bit. And then we use that to provide the SDS loss for Dream Fusion. So when we do that, it can still generate a 3D consistent object and looks a little bit, just a little bit like your input subject, but not quite. And then we use the full Dream Booth fine-tuned model to do an SD edit image-to-image translation to basically add noise to the partial Dream Booth Dream Fusion results to translate them into images that look more like your subject. And remember that the viewpoint here is quite good. We haven't really overfit to the viewpoints because we did a partial Dream Booth. So after we do this, we then use this bigger set of images that cover more viewpoints to do another Dream Booth, to do the multi-view Dream Booth. And then we use that to provide the loss to Dream Fusion to do the final NERF recovery. So after that, the results do look much better. Again, the subject fidelity is not perfect, but it's a really good, I would say, a first attempt at this problem. So you can see that the dog, this is the dog, the cat, and an owl. This is some comparisons. On the left of the three columns are just a straightforward combination of Dream Booth and Dream Fusion. And on the right are the results of Dream Booth 3D, which is this iterative method to recover the 3D NERF representation of the subject. So we did some user studies, but I think the thing that to pay attention to on this slide is that there are three things we care about in this application. One is 3D consistency. It needs to look like a true it needs to look like a consistent 3D recovery. And second is subject fidelity. It needs to look like my subject, my dog, my product. And the third one is prompt fidelity. It still does need to preserve the ability to follow my text prompts. If I want to generate the subject in a variation that I intend, it needs to follow that text prompt. Showing more results and also applications. So in this case, we are changing the material of the subject. Again, the subject fidelity is not 100%, not perfect, but pretty good, I would say. And this is an example of showing how you add a tie, add an umbrella to the subject. Or you want to change the color of the subject. Or you want to change the pose. So you get the objectives are you get the subject fidelity, and you also can generate these novel variations and renderings of your subject. So that was Dream Booth 3D. And the third work that I'm going to talk about is, can you do this for style? Can you personalize your image generations to specific styles? So this work is called Style Drop. This work was led by Kyuk Song and Dilip Krishna and others. So on the left are the input images showing you the style that I want to reproduce. And on the right are the results. So there has been a lot of style transfer work in the past, but we felt that there was something missing. We wanted to basically do a modern take of this problem. And the three things that we want, the three objectives we have. One is that we want the method to have excellent disentanglement of style and content. We want to be able to apply a given style to any content. And also, we really want to grasp the style on the system level. So not just texture, but basically both the form and the soul of a style. Using a Chinese idiom is 形神兼备, both the form and the soul. We want to capture both. So I'm first going to show you some results. Kyuk has generated a lot of just amazing results, and then I'm going to talk a little bit about the method. So on the left is the input, and on the right, these 8 images are the results. So in this use case, actually, there was only one input image that was presented as input. So it was pretty remarkable that it could generate images of that style with great adherence to the essence of the style. So in this example on the left, there are 6 input images that were presented as input to capture that style, and on the right are the output images generated using that style. Again, just pages and pages of results. Again, on the left are the input, on the right are the output. This one is a watercolor style, and you can see that the generated images not only captured the watercolor, it also captured the paper, the variations on the paper, and it did spelling of these it did letter generation, and these are just more results. So in the next few pages of results, you can see the association of style with content. So for example, at the top left corner is a penguin and also a banana, and on the bottom right is an avocado. It's like these content in this style, and then it's the same content in the same layout. For example, the top left are the penguin and the banana, and the bottom right is the avocado, but in a different style. Again, penguin, banana, and other things, avocado in a different style. Again, in a 3D style. Just pages and pages of results. In this case, it's a children's drawing. You can see that it really captured the essence of the style pretty well. And this is another result. So how was it done? So there are a few elements that we thought were important to the results. The first one is that it was done on this text-to-image model called Muse that I'll cover a little bit later. It's a mask transformer model. It's different from a diffusion model, but it has its advantages. And the second element is parameter efficient fine-tuning. So remember when I talked about Dream Booth, that was like full fine-tuning of all the weights. But in this case, we used parameter efficient fine-tuning, in this case, adapter tuning, but there are other parameter efficient fine-tuning also. You can think of them as sort of a non-destructive way of fine-tuning. So most of the model weights are kept unchanged, but you add a small number of new weights to try to capture that style. And then the third element is the text prompt construction associated with the input images. So we used text prompts that describe both the content and the style. So in this particular example, the text prompt was a cat in watercolor painting style. So it described both the content and the style. So it helps so these are text prompts constructed for the input images for the adapter fine-tuning. So if we do it this way, it helps the disentanglement of style and content. And the fourth one is iterative training with feedback. Sometimes when only one image is presented as input, sometimes it does have leakage. So for example, in this use case, in the example at the bottom, so the style reference is this style of this house. So when we only use this one image to fine-tune the model, you could see that when we tried to generate a chihuahua in the style, the house, the content of the input image leaked into the result. So, but the two images on the right are pretty good. So basically, so a human could say that these two images are good. I'm going to add these two images to the training. And then it's an iterative process. People do that quite a bit in language model training these days. So then you get, after that iteration, you get very good results shown on the right. And you could also combine style drop with Dream Booth. So now you can generate images of the specific teapot in different styles. So next I'm going to talk about Muse. This work was led by Hui Wen Chan and others. So it's a text to image model It's not a diffusion model. It's a masked transformer model, but it could be interpreted. It could be understood also as a discrete diffusion model. So how is this different from other text-to-image models? So first of all, it's pretty fast. It uses this parallel decoding method first proposed in this paper, also led by Huiwen and Lu and Han, called MaskGit, which uses a parallel decoding method that makes it very fast. It also has very high fidelity to the text prompts. Also because it's trained with the impending objective, it comes with some really nice editing capabilities out of the box. Again, I think one of the key ideas in this is the parallel decoding originally proposed in the MaskGit paper, which basically says that, look, there are some text-to-image models, for example, PAR-T, that uses autoregressive method that predicts image tokens, just like how you do language. You predict the next token given the previous tokens in a scanline order, but images are not constructed that way. Images do not behave that way. So we want to predict image tokens based on all the image tokens around it in parallel and in a few iterations. So that was like a really great insight. And that also enabled Muse to be a very good text-to-image model with fast speed. So when it was published, it was an order of magnitude faster than the other models. But of course, I think with diffusion, there's now also distillation, progressive distillation, which also makes it faster. So everybody's making great strides, and we're getting very close to great applications. So these are just some results of generated images from Muse. It comes with out-of-the-box editing capabilities. This one's mask-guided editing. This one's mask-free, instruction following text-guided editing. So on the input image is the one on the left, and the others are edited images following the text prompt. And because it's pretty fast, so you could actually do interactive editing. So this one is an example of interactive editing recorded at real speed. So the text prompt is change this to white wine, and then it changed the glass of red wine to white wine. So we did release this as part of the Imagine family of foundation models released in Google Cloud. So for example, this is an example of using the model to generate a handbag image and then to edit it with text, and then also to dream booth it with adapter tuning to personalize the generations of the handbag placed in different settings. So in the end, I want to show a fun example, a fun application. So this is an application called IO Flip. This was a card game that was released during the Google I/O halftime show. So it's a Pokemon-ish card game. So you can choose your mascot, and you can choose the setting or what it should look like. And then we generated all the images in this card game are generated, and then we play this. For example, in this example, the input character is this little character at the bottom, and all of the card images are generated with Dream Booth on Muse. I'll just show a quick.
Got me where you want me,
So, whoops. So the images were generated by us, but not the 3D. But we would like to do 3D as well. So we want to make enough progress in the 3D, in the personalized 3D generation of specific characters so that you could also make game characters just by providing a few input images. Okay, that's it. Thank you.
All right, and Yuanzhen will be around to come and say hi too. The style drop stuff looked amazing. Okay, we have now a speaker on Zoom. This is Jinggang.
Hi.
Hi, Jinggang.
Hello. Yeah, could you hear me?
Yes, I can hear you. What about the room?
Okay, let me share my screen.
Should I start the introduction of the speaker?
Please do, Lingjie.
Oh, yeah. Hi, this is Lingjie Liu from UPenn. It's my great pleasure to introduce our next speaker. I think it's also our last speaker, Xingang Pan, who is also my close collaborator. Xingang is an assistant professor at the School of Computer Science and Engineering, Nanyang Technological University. Prior to join NTU, he was a postdoc researcher at the Max Planck Institute for Informatics, advised by Professor Christian Thielbert. Before that, he received his PhD degree at the Chinese University of Hong Kong in 2021. His research interests include generative AI and neural rendering. Today, Xingang will introduce JetGAN, which has attracted tremendous attention from researchers, artists, and designers since its release. Welcome, Xingang. We are all looking forward to your talk.
Thank you, Lingjie, for the kind introduction. Yeah, good afternoon, everyone. So it's my great pleasure to present our recent work, Drag Your GAN, Interactive Point-Based Manipulation on the Generative Image Manifold. This work was done when I was a postdoc at Max Planck Institute for Informatics and Saarbrücken Research Center for Visual Computing Interaction and AI. And this is also a joint work with MIT, UPenn, and Google. So to start with, let's take a look at the current status of image manipulation. Thanks to the development of deep generative models, a lot of image manipulation methods have been proposed in recent years. For example, supervised learning uses manual annotations to tell the model how to edit attributes. And some methods allow users to edit image based on a semantic map. To control human pose, we can use 3D human prior as a guidance to the generative model. And recently, text guidance has become a popular way of manipulating image due to its flexibility. These are just a few examples. So these methods are pretty good at controlling certain attributes, especially semantic attributes. But when we manipulate an image, we not only want to control what we generate, but also where we generate, like the layout, position, pose, expression, and shape of the object that we generate. However, these current methods have certain limitations regarding editing these spatial attributes. For example, supervised learning can only edit attributes where it have annotations, which is not flexible. And semantic map is convenient in editing shape. But if you want to rotate this car by a certain degree or change the pose of a human, that means you would need to repaint the whole semantic map, which is not that convenient. And human prior can only control human, of course, but not other objects. Text guidance is flexible, but it's not very precise regarding control where pixels go. Like if we want to, let's say, move the head of the cat towards left by 10 pixels, the language model may not understand how long is 10 pixels in this image. And it is also constrained by the text model's capability in understanding command. So in a word, these existing methods lack flexibility, precision, or generality in spatial attributes manipulation. So is there a better way to control spatial attributes? A good example is an ancient way how people create visual content, which is shadow play. So in shadow play, the puppeteer only need to control a few control points to change the pose of the figure. So as you can see, this type of control is very intuitive, flexible, and precise. So an interesting question is, can we let users control image contents just by dragging control points like in shadow play? A related function in commercial software is liquify in Photoshop. So here user can warp image locally with the cursor. But this editing is just a simple 2D warping, and it cannot create new content like hallucinating the occluded area. A related line of research is shape deformation in computer graphics. So here shows a classic method as rigid as possible deformation, and users can drag the object to deform its shape. But this type of methods usually have certain assumptions on the rigidity, like a uniform rigidity assumption. And it also cannot hallucinate new content. So in order to overcome these limitations, the model have to have an understanding of the structure of the objects and be able to synthesize new content when needed. That leads us to deep generative models. So in this work, we decided to start with generative adversarial networks, or GANs, due to its nice editing property. So after training, a GAN generator basically maps a low-dimensional latent code to a high-dimensional image. So in this sense, GAN can also be seen as modeling an image manifold, as it finds a low-dimensional basis for describing high-dimensional data. A nice property of GAN is that we can change different attributes of the image by traversing in the low-dimensional latent space. So our goal in this work is to achieve interactive point tracking operation on the image manifold modeled by a GAN. So for a GAN generated image, we want and a user dragging operation. We want to edit the latent code such that the image deforms following the user dragging command. So a key question here is, how should we edit latent code? And the advantage is that because of this GAN prior, it can deform the image following the object structure and be able to synthesize new content. Before we go into method, let's take a look at how our method works. We allow user to optionally input a mask defining the movable regions, and users can just click a few control points and their corresponding target points. The method will move the red control points to the blue target points. So now let's look at the overview of our method. For a GAN generated image and the user input handle points, we first supervise the handle point to move towards the target points using a motion supervision loss that optimize the latent code by one step. So after one step optimization, we would get a new latent code that produce a new image where the object has moved for a small step. But so far, we don't yet know how much the object has moved. So we need to perform point tracking to get the new location of the handle points. So based on the new handle point position, we perform motion supervision over again. And our method iterate between motion supervision and point tracking until the handle points have reached their target points. So in the next, I will introduce motion supervision and point tracking in detail. First, I would like to share our preliminary attempts in motion supervision. So in order to supervise motion, our initial idea is to leverage a model that captures motion. And one obvious choice is optical flow model. So for a GAN-generated image, we make a copy of the current image as a reference image. We send two images to optical flow model to estimate the optical flow. Here we use the raster model. Because the two images are the same, the optical flow would be close to 0. So our goal is to supervise a handle point. Let's say we want to move it towards left. In order to do so, we look at the optical flow of this handle point. So initially it's 0. If we want to move the handle point to left by 1 pixel, it means that we want this optical flow to be -10. So we use this target optical flow as ground truth to supervise the predicted optical flow. And because everything in the pipeline is differentiable, we can optimize the latent code with this loss. And this strategy works. So when the target optical flow is reached, it does move the image by a little bit towards left. So that's great. However, here we use an additional optical flow model, RAFT, which is an iterative model that introduces a lot of computational costs. And because we want to do interactive image manipulation, we hope that our algorithm can be efficient enough for user to get the results in a short time. So we start to think, can we get rid of this optical flow model? So our idea is that the feature that this optical flow model estimates is essentially a feature that is sensitive to the spatial information or discriminative to the spatial information of the image. And actually, some previous research have shown that the GAN features are also discriminative enough to be used for few shot or unsupervised segmentation and even dense correspondence distillation. So these are evidence that GAN features are also discriminative to spatial information of the objects. And this gave us hope to perform motion supervision and point tracking directly in the GAN feature space with simple and intuitive designs. So now let's look at our final method. So here shows an intermediate feature of StyleGAN2. We use the 6 StyleGAN2 block as the feature here. It has a resolution of 256. So we bilinearly interpolate to have the same resolution as a final image. In order to move the red handle point to the blue target point, our idea is that we look at a small patch around the handle point, and we want to move it by a small step. That is to move to the position of the blue patch. And to achieve this, we supervise the blue patch to mimic the feature value of the red patch. So you can think of this in this way. If the value of the blue patch becomes those of the red patch, it means that the red patch have moved to the position of the blue patch. So essentially, this loss drives the red patch towards the blue point. Importantly, we need to detach the red patch from the backpropagation graph to make this gradient unidirectional. And recall that we allow user to input a mask defining movable region. So we apply a feature reconstruction loss in the remaining areas, as shown in the darker regions of the feature map. Good. So we use this loss to optimize the latent code for one step. This gives us a new image and a new feature map. So our next goal is to perform point tracking. Suppose that the feature of the initial handle point is F0. We search in the new feature map for the nearest neighbor of F0. So essentially, we find the we perform point tracking just by feature matching. And because GAN features are discriminative, the pixel we found in this way tend to semantically correspond to the initial handle point. Let's say if the initial handle point is in the line of the in the nose of the line, then the new pixel we found with feature matching is also likely to be on the nose. So this concludes our introduction of motion supervision and point tracking. Our discuss is based on a single point. For multiple points, we just sum up all this motion supervision loss, and each point is tracked independently. We iterate between this motion supervision and point tracking until it reaches the target point. So with this simple but effective design, we can edit spatial attributes of many objects, like change the pose of a dog, or redesign the shape of a car. Car designers might be interested in such feature. Or you can rotate a car, or edit other animals, and even close only one eye of a cat, or edit elephant's nose. You can edit human face, of course. Or change the pose of human and adjust its clothes. Or any strange things like microorganism. Landscapes, you can make a sunrise if you want. So there are a lot of spatial attributes we can control in this based on this point-based dragging operation. So during this project, there came out a related method called user controllable LT, or user controllable latent transformer. And it did a very similar job as ours, but unlike our optimization-based methods, this method trains a transformer that takes everything as input and directly predict the latent code that gives the desired edit. So it only needs a single forward pass and it's fast, but this comes at the cost of performance drop. So this table summarizes our differences. Firstly, user controllable LT does not perform point tracking, so it cannot accurately move the handle point to target point. It can roughly follow the user guidance. But our method can do this. And second, this method cannot keep certain regions fixed. It does allow user to input a few anchor points, but in practice, no obvious movement can still be observed. And in our results, we fix the background much better. And the GUI cannot support more than one handle point, but our method can achieve this. Theoretically, the method can support more than one handle point, but the performance is not satisfactory. The advantage is that they're fast, nearly real time. And our method, as an optimization-based method, it takes a few seconds to finish one edit on a 3090 GPU. But I guess this is acceptable for most users. So here shows qualitative comparison. The first row shows the input image and the user dragging operation. And the next two rows are results of user controllable LT and hours. So our method achieves more precise and reasonable editing results than the baseline. From the first column, you can see that we successfully moved the 3 control points to the target. So this corresponds to the head, leg, and tail of the horse. But the baseline method fails to do so. And at the last column, we drag the sound towards left. And interestingly, the specular highlight on the C also moves along with the sound. It shows that the generative model captures such correlation. But the baseline method tends to change the whole image. So you may wonder how our method performs on dense control points. So here we perform dense face landmark manipulation. We randomly generate 2 face images using a pre-trained StyleGAN2 on FFHQ. So our goal is to edit the landmarks of the input image to those of the target image. And as you can see, our method successfully moves the landmarks to match the target. And this edits the expression and shape and even pose of the input image to match those of the target. So we compute the landmark error between our edited results and the target face. So apart from user controllable LT, we also compare with 2 additional baselines, tracking baselines, including raft tracking, which is essentially accumulation of raft predicted flow. And another one is PIPS, which is a recent point tracking method, also came out during this project. So we replace the point tracking module with these 2 tracking methods as a baseline. So it can be seen that our method have the best performance among all methods, and the error is significantly lower than user controllable LT and raft tracking. And because we don't use additional tracking networks, our method is much more efficient compared with using these 2 tracking methods. Another quantitative study we did is paired image reconstruction. So for a random GAN-generated image, let's say image A, we add some small perturbation to the latent code to get another image, image B. So A and B have slight differences. We calculate their optical flow and sample a sparse set of this optical flow. Here are 32 pixels. We take sparse flow and image A as input to our point manipulation methods to estimate image B. So the better the point-based manipulation method is, the better estimation of B we would get. So we compare the estimation of B with the ground truth B as the final metric. The results is consistent as before. Our methods have the lowest MSE and LPIPS reconstruction error among different object categories. And here shows the point tracking qualitative comparison. On the left is the input image and the user dragging operation. The first column shows our method, where the handle points accurately track the object. So it tracks the points right above the nose of the line. But PIPS and raft suffer from some drift during editing. And as a result, they cannot accurately move the nose to the target points. So far, the results we've shown are on GAN-generated image. But for image editing, an interesting question is, can we apply to real image? So for GAN, this can be done by GAN inversion. So we optimize the latent code to reconstruct a given real image. and then perform editing in a similar way. So here shows some real image editing results on face, animals, and cars. We can edit diverse spatial attributes by point dragging like before. So this point dragging goal can be ill-posed. For some dragging, there could be multiple solutions. For example, let's say we want to move the nose of the dog towards right by some extent. We can achieve this by shifting the whole dog, or rotate the whole dog body, or rotate just the head of the dog. And in practice, the method would tend to reach a solution in the image manifold that is closest to the initial image. In this case, it just rotates the whole dog body. Users can always introduce additional constraints. Like if you want to change only the head, you can draw a mask on the head, then it will only rotate this dog head. And sometimes users can also create out of distribution manipulations that goes beyond the scope of the training data. For example, you may aggressively open the mouth of the line. And in these cases, sometimes our method produce some not perfect, but reasonable results. Like the tongue and teeth in the line mouth are reasonable, although there are some distortion artifacts. And the more aggressive the edit is, the more likely it would produce some distortion artifacts, like the wheels of the car. For StyleGAN, there are two different choices for latent space. One is W+, and the other is W. The W+ space is less constrained, so it's easier to reach some out of distribution manipulation, like close only a single eye of this cat, but W space fails to do so. There are several limitations of our method. The first, as mentioned before, for aggressive out of distribution manipulation, it's prone to distortion artifacts. For example, this StyleGAN human model is trained on a fashion data set where the man or woman are basically just stand with hands down. So in this case, if you create some significant out of distribution pose like this, it will likely cause some distortion artifacts. The second is the selection of handle point. So if you select a textureless handle point, like on the flat red area of this door of the car, it's more prone to drift during tracking. So if you look at the relative position between the handle point and the rear view mirror, you would see that it moves towards the front of the car. It drifts towards front of the car by a little bit compared to the rear view mirror, which is not what we want. But if the handle point is on a texture-rich area, like on the rear view mirror, it will track the object more accurately. I think the most important limitation is still the editing of complex real images. So both GAN training and GAN inversion favors simple images, like what we were shown before. There is a main object in the center of the image and somewhat clean background. But for images with a lot of content like this, it's extremely hard to train the GAN and to perform GAN inversion. And I think how to extend the method to complex real image is an important future direction. So to summarize, in this work, we propose DragGAN that allows users to control image interactively by specifying point movements, just like in shadow play. And to achieve this, the key components are motion supervision and point tracking, both of which are enabled by discriminative GAN features. So what's the role of this dragging manipulation compared to text-guided manipulation? So I believe that these two are complementary. The text guidance are very flexible in controlling semantic content. But in order to edit spatial attributes, interactive point-based dragging is more flexible and precise. So ideally, an image manipulation AI system should support both functions ultimately. So that's all for my presentation. Thank you very much.
Thank you very much, Xingang. We have a question on Zoom for you.
Yeah.
Can you elaborate on the impact of different feature map choices in the motion supervision and point tracking steps? How sensitive are these choices to variations in dataset?
Yeah, so we have an ablation study on this, on the face landmark manipulation experiments. So what we observed is that we tried the 5th, 6th, and 7th feature maps and even a combination of them, and we do not see strong effects of different choices. So the performance are all satisfactory, but choosing the 6th block performs slightly better. So we just use that one. But if it goes to very different feature map, like the very early stage feature map, you would have so small spatial resolution, so you cannot accurately localize the point. Yeah, so that's what we observed.
Thank you. Okay, it looks like there are no questions from the audience. So there's one last one on Zoom. Do you think it's possible to extend the techniques to diffusion generation since it mainly uses feature tracking?
Yes, so I believe this is an important next step. And I guess the main challenge is not in point tracking, but in motion supervision, because diffusion models have a very different property as GANs. So it have a different latent space. It's a spatial noise map, and it's an iterative image generation process. So I think it's not very straightforward to apply drag GAN technique to diffusion models due to the different properties. But maybe there are some insights or high-level ideas that can borrow, like some feature-based motion supervision, but this still requires some exploration, I believe.
Thanks. Okay, let's thank Xingang again.
Thank you very much.
Okay, at this point, we have a treat for you. Vancouver is known as a home of many creative arts, such as visual effects, animation, and video games. And so we have put together a panel of 3 esteemed, let's call them artists. Some of them genuinely are in all aspects of this work. So please could I invite Larry and Carl and Daryl to come up onto the stage, and we will just switch over. So our panelists will be able to tell us what many of these techniques are going to mean for industry that actually has to do work to produce very specific, tailored content. And we will gain an insight into their hopes and fears of AI in practical content generation. So just give us 2 minutes and we'll get set up. Okay, do we see this on the screen? AV folks, please can you help out? Okay, so let me introduce to you Larry Gritz, Carl Jarrett, and Daryl Anselmo. I asked them each to present just 2 slides to introduce themselves and the context with which they've been sharing the day with us today. So we're going to start from right to left. Okay, your mics should be working. Daryl, if you would like to say hi, your slides are now on.
Is it working?
Yeah.
Great. Hi, my name's Daryl Anselmo. I am an artist and an art director. I've been in the video games industry for about 25 years. I've worked at Electronic Arts for a number of years. I was the co-creator of NBA Street, Def Jam Vendetta, Def Jam Fight for New York. I've started a couple of companies. One of them was sold to Disney. Another one recently exited in 2019. So I've been taking some time off and exploring the wonderful world of Gen AI. And mostly, this is some of my latest work. And one of the things that I'm doing here is using ControlNet and DreamBooth to do some geometric and architectural explorations. Thanks.
Thanks, Daryl. Carl?
Yeah, hi. My name is Carl. I've been in the industry for probably about the same amount of time, about 25 years. I started in cartoons, and as you can see, I worked on some pretty interesting titles about 20 years ago. But yeah, I've been in the art space, digital art space for almost 25 years, like I said. Right now, I'm at EA. We're working on quite a few different things and exploring how AI, generative AI, stable diffusion, and that type of technology is going to help push us forward into the future and just make better experiences for our players.
Thanks, Carl. And Larry?
Thanks. Now I have to remember what I wrote on my slides because I can't see them all. Hi, my name is Larry Gritz. I'm a software architect at Sony Pictures ImageWorks. We are primarily located in Vancouver, but also have offices with a number of people in both Los Angeles and more recently Montreal. We are a large visual effects and animation studio for film. We're a little bit unusual in that we both do entire animated feature films, but also visual effects for what most people consider live action movies. And can you, I have a short reel just to give you some idea of some of our recent work, if that works. So I hope your imaginations were working well to supply the sound for that reel. But yeah, so a long time ago, I was working more on the art side. I have done lighting and look dev and other such things on feature films, but the majority of my career is on the research and development side. I have a PhD in computer science. My specialties have tended to be in the areas of like realistic 3D rendering, shading, lighting, image processing, that sort of visual computing angle of things. As just as a representative project of that, I'm the designer of Open Shading Language, which is the sort of de facto standard shading language used for high-end film work. I got a Technical Academy Award for that work. And one of the things that I do as as one of the leads in the large software department that we have at the moment, is I'm actually helping on the AI strategy for the studio. Like, which technologies do we think are going to? Oh no, I'm good. I'm good. Thanks. Yeah, I got it. Which technologies I think are going to be useful where, what to invest in, yeah, how to pursue it and do it safely and helpfully. This panel was really appealing to me because it's sort of right at the heart of where my head is right now and what we're looking at as we sort of go off on our AI journey.
So I posed our panelists 5 or 6 questions to get the conversation started, and then we will open up the floor to Q&A, okay? So here we go. The past 2 years have been eye-opening for many people in the creative arts, for better and perhaps for worse. So what have been your and your team's impressions of this recent rapid progress in AI? Go for it.
Yeah, I don't mind going. Yeah, it's been really interesting. We have hundreds and hundreds of artists at our company, and obviously with the advent of things like Midjourney and DALL-E, it's obviously something concerning when people first learn about what's possible with these technologies, especially with concept artists and so forth. But I think what's interesting is, as people become more and more familiar with the latest in technology, we're starting to see more about how it's going to unlock the ability for us to do more with what we've got. Not necessarily have really tiny teams that build these great, big, expansive game experiences, but actually use the people that we have to actually leverage technology and build broader, deeper, wider, more creative experiences, which I think is something that we've struggled with, in the past, like we as in the greater video game industry. But I think people are cautious, and I think there's a lot of people who are, somewhat trepidatious, but I think there's a lot of excitement too.
Yeah, I'm quite excited personally. I think probably my first real aha moment was Midjourney about just over a year ago, and then I immediately sort of entered the peak of inflated expectations, and now I'm seeing that the more people that I talk to in the industry, sort of a lot of producers that I talk with specifically have very big expectations for where things are going to go. But the more that you use the technology and see what it can do, and what it's good at and what it's not good at yet, the more realistically that I'm starting to see where this fits into production pipelines. And I think it'll probably be, there's this particular production cycle that's happening right now. I think it'll probably be the next one where you really start to see it being built in from the ground up into production. So I think a lot of productions right now are building off of their legacy code bases or building off their legacy asset databases.
Yeah, I would say that myself and most of the coworkers that I talked to we're actually quite optimistic about this, and at the very least, like just like everyone else out there in the world right now, we follow this very closely. Like there's an internal chat room that we have where when people see the revolutionary things that seem to happen every day, we're sharing the links and we're talking about can this help us in this way? Is that going to work? How do we try this? I would say that, there's a little bit of trepidation sometimes, but the overwhelming thing that I'm seeing is people kind of chomping at the bit of like, when is this technology going to be ready in a way that we can actually use it to do real work? Sort of moving beyond the demoware to the, something that we can actually use. But overall, like people are super enthusiastic about the prospect of it.
Okay, let's talk practical. CVPR, we often focus on images because that's easily accessible data to us, and we produce lots of very nice, let's call them demos. But making high quality content is work with exact constraints, many intermediate steps, specifications. So do you see any ways to integrate current AI technologies into your work? And have you seen any examples of success or failure?
Yeah, I can jump in. One of the jobs that I did years ago, I worked at Zynga for a number of years, and I was the art and creative director on Farmville 2. And that particular game required content tonnage. We were putting out 7 or 8 buildings every week. We were putting out 10 to 15 animals every week. And the content that was being produced for that particular game was being consumed at a very rapid pace. I followed that up with a game that was in the Unreal Engine that was a shooter that was more higher fidelity, higher production value, very polar opposite productions. The most recent product that I was helping with was a mobile game. It was a little bit closer to the Farmville world. And unfortunately, I can't share any of that work. It's still under non-disclosure. But I was using ControlNet and Stable Diffusion and Dream Booth to rapidly produce a lot of content that is similar to the Farmville level of fidelity of content. And it was doing what it needed to do. You know, it was quite. I was able to get a level of artistic control. I was able to produce a lot of output in a short period of time. If I was to contrast that with working on a first-person shooter in the Unreal Engine, content production for those games is quite onerous. You know, it's a high fidelity model, low fidelity model that needs to be retopologized. There's many steps along the way in order to get your content running on consumer grade hardware. That is where performance is very important. Latency needs to be really low. Frame rates need to be very high. And I think I would struggle to integrate it into those. And I'm interested to hear what Carl has to say about that and what Larry has to say about trying to integrate the current set of tools into production pipelines today in high fidelity games.
Yeah, I think it's interesting, right? Like there's AI tools that could do just about anything these days, or at least are attempting to do that. So, you know, I think there's a multitude of ways where, you know, in gaming, I think we're already using AI in certain areas. I know Adobe's got a few different tools that are already available in Photoshop that are, you know, ML based and so forth. You know, but when I think about it, like, you know, at EA, we make a lot of video games that have a lot of realistic humans in them. And you know, I think as an industry, we spend so much effort trying to create realistic humans that it overpowers our ability to really focus on creative, on delivering great stories. So I think like that's really where I think we're going to see big leaps and bounds is, you know, being able to create like the foundation of what any game really needs. And then, you know, using those tools to really, you know, unlock the creativity of the teams that we've got and the individuals that are on the team that have, you know, ideas that, you know, AI might not be able to generate. And hopefully we can, you know, steer things in that direction.
Yeah, let me just say 2 areas that we have been using AI tools lately. One of them is for what we call digidoubles. So on the live action visual effects films, a lot of the times, one of the first things that we'll do is, you know, we'll send the actors into the scanner, you know, get good 3D results, because there's always going to be, you know, stunts that are too dangerous to do, or situations where, you know, it's just easier to make a digital version of them than it is to try to, you know, film the action sequence, or sometimes there's, you know, late in the production, they want to change a scene and they don't want to get the actors back on set. But there are lots of reasons for this. But like one of the things that used to be, you know, quite difficult to do, and still is you know, you have a stunt double who's done some action and you want to put the real actor's face on it. And this used to be a very, it still is for the most part, like a really complicated, like 3D, you know, problem to solve. With all the, you know, match moving and then 3D model in the face. And we just started to tinker with using some deep fake technology for this. And it doesn't always hold up for like hero shots, but there are certain, you know, stunt face replacement kind of things where actually the tools are getting to the point that it's passable. And sometimes that's just the easier way to do it. So that's one place where things have actually gotten into production. And another is on the animated side. The first Into the Spider-Verse movie that we did, it's a very stylized film. It's got a very graphic style. One of the important elements of that is like line drawings on the faces and outlines and things like that. And it's a big part of the look of the film and the feel of the characters. But they're not textures. They're not like stuck to the face. It's more like a graphic style where like there's a stylistic aspect, an artistic aspect to how you would place these things. It depends on the pose of the character and where the camera, is relative to the face and things like that. And these things were actually it's all done in 3D. It's 3D geometry and then made to look 2D. And it's extremely labor intensive. And on the first movie, actually a super clever effects supervisor decided like maybe this is a place to use a machine learning approach, and actually had artists do a bunch of the line placement, the feature line placement for a variety of poses and a bunch of different camera positions, trained on that, and got it to the point there where actually for new shots we could run it through, use the inference to do all of the initial placement, and then the artist could fine tune it to get it right. And it was like one of those like get you 80% of the way there kind of solutions, but 80% of the way there for something that's like a huge labor sink, that's a lot. And so that's a place where we really did use machine learning techniques, I think, to great effects, and we're looking for other applications like that.
Yeah, I think the labor point's really important, is like, using AI to really fast track anything that just takes an enormous amount of human power to achieve in any of our products, whether it's facial animation or, in video games, you tend to want to create interactive experiences, really broad experiences. So, in film, it's linear, right? So you're capturing a human and putting VFX around them, creating a scene. It's meant to be watched from start to finish. Whereas in games, you really want all of that capability, but anywhere and anytime. And you want to have NPCs that you can talk to and interact with, that have non-scripted things that you could say to them or respond from. And so I think that, the real benefit of what we're looking at here is really just bringing down the cost of some of these things that are so prohibitively expensive, especially in the interactive space. Facial animation, text to voice and voice to face and all that sort of stuff, I think is really exciting, because it's going to just unlock our ability to, like I said before, build better story and something that's more engaging with our audience.
Thank you very much. Well, speaking of the question of control, how human creators interface with AI is critical in this domain. Some people say that humans will collaborate with AI, whatever that means. So how do you see the role of AI in this potential collaboration with artists and designers?
Yeah, this is something we think about a lot. I mean, we're a very artist-driven company. We're not really after replacing the artists or anything like that, but we are interested in, I think the word like collaboration with the artist is really a very good description of what we're after. And I think a lot of art, you can say that it's never really finished. It is merely abandoned when you run out of time and the deadline's hit. And that's I'm sure it's true in games too. It's very true in film. So anything that we can do to make that time more productive is super valuable. And sometimes it means shortening the schedule. Sometimes it means things that were just too big for the number of people we had or too expensive we could do. Sometimes it means you keep all of that, but you can just get more iterations in. And that is really important to sort of getting everything to the quality level that you want and having a lot of creative decisions. So like I kind of view like where AI tools fit into sort of three broad categories. One is what I would call computer graphics, like the stuff that appears, on the screen when you see the film, the imagery, the movement, that sort of thing. So that's where like, anything that's making images directly that you're going to see in the end sort of falls in there. The second class of things are like what I like to call ideation tools. So like more like when you're doing the design phase of things, you're trying to get to what the look of the film is going to be and how you want things, like you're in the production design phase. And there's a lot of iteration that goes on there. And a lot of times the creative leads of the film will come to us and they won't know what they want quite yet, right? They're good at recognizing when they see things on the right track or when they don't like it, but they're not always good at describing what it is they want. And so we go through a lot of cycles of like, they'll say like, oh, look, we think we want this, we think we want that. And you send the, concept artists off to do a bunch of art that come back for a review in a week. And they're like, oh, no, that's not what we want. Things where we could sort of tighten up that iteration loop to where we can much more rapidly explore design space is also super valuable, even though none of that stuff will appear directly in the final product. But that's what gets us conceptually to how we know what we want the design of the film to be like. And so that's a big class of tools there that that we're very interested in, even though it's not a final image result kind of thing.
Yeah, I want to dig into the collaboration and where the artist sort of fits in versus where the AI is kind of taking over. I think, if I lean back and think about my experience working with other animators in the past or artists, and as an art director, often I use the word choice. And so I'll say, I really like the facial expression that you chose there. I think that was a really good choice. Or I like the way the wrinkles are folding off of that particular character. You made a very good choice with that paintbrush. And so, on one end of the spectrum, if I just type in a few words into Midjourney and get an image out of the back, there was a couple of choices there that I made when I entered the text. Perhaps I'm trying to craft a specific image, but there's other and that may be one end of the spectrum. On the other end of the spectrum, there's ControlNet, for example, where I've created the exact layout that I want. I'm using canny image guidance, or I'm using a pose from a character from using open pose. Those are artistic choices that were deliberately made. And so now I'm letting the AI do the heavy lifting, as opposed to, and so that's a different spectrum of choice. And I think that's one lens that I want to look at this conversation through, really, is the question of choice and where an artist has made that choice versus where the machines have made that choice. And it's not always apparent in the final work.
Actually, I don't mind. I want to touch on something maybe slightly tangential to that. Is like, I think, AI is going to allow this level of democratization of technology and tools, right? I think if you look back, in our industry, 20, 25 years ago, it's like a lot of the people that started in the industry were somebody who knew how to use that software. Like, they might not necessarily have had like a very creative background or an artistic background. And a lot of people who are very creative and artistic don't necessarily have the technical skills to translate over to, building beautiful art on a computer. So I think what AI is going to allow us to do is really help creatives, help artists get to their idea faster. Like to your point around choice, it's like, how do I give them an interface that they can interact with this technology to create things of their choosing, create things that they can envision in their head. And I think that democratization is really going to, change our landscape, at least. I imagine it's going to affect everybody, but, just opening the door to people being able to really express themselves with, computer graphics and whatever else ends up in the entertainment space in the next 20 years.
Okay, I'll have one more question for the panel, and then we'll come to questions from the audience. But this one you might want to pay attention to. So this is probably going to be your next research paper. What's one problem in your work or pipeline that nobody likes doing, but that AI might be able to solve?
Retopo.
Sorry, what's retopo?
Retopologizing. So taking a high fidelity ZBrush mesh and turning that into a performant game object. The other thing is, if it could just look at my Unreal scene and just rename everything for me, just rename all my textures, rename all my files. That would be fantastic. So like a linter would be a phenomenal tool for me. And then UV unwrapping can be quite onerous in high fidelity modeling. So those three come to mind. There's many more.
Yeah, I mean, I think we could probably list out just about everything we do that could be made better with AI. I think there's a couple major pain points. I already touched on one, creating digital humans. I think we all we all struggle with that. You know, I think stylized games are one challenge, but things that are trying to create realism in just the interactive space. We just, like I said, we spend so much time and effort trying to create good looking digital humans that do all the things we need them to do in game. So any technology that's going to allow us to do that. You know, speaking video games specifically though, you know, FIFA and now FC is a pretty big game. If you think about how deep that game's menu system is, there's parts of that menu that are probably 5 to 7 years old. You know, the team, as massive as it is, can't afford to rebuild the UI every year. So if I don't know if you saw the paper about an hour ago, but you know, people are looking at, you know, technologies to increase our ability to create good GUIs, good user interfaces for interactive experiences. So I think again, that's going to be something that's going to save huge amounts of time and effort.
I thought really hard about this question and what I wanted to put on my wish list when I was in front of you. And I really struggled, but I want to come at it from a slightly different standpoint and ask you to reconceptualize something instead of just asking for a specific thing. So one of the things that you have to understand about the art that's done at this kind of scale is the degree to which it's really heavily art directed. Like one of the problems that we see with a lot of the AI demoware out there is it's presenting a final answer and it's kind of a black box, right? It's like, if it got you exactly what you wanted, great. And if not, then what are you going to do? What's the plan B? And there's often not a plan B. And that's a big, one of the big barriers to us in incorporating some of this technology more is, you know, what happens when it fails and how art directable is it going to be? So like, as an example, just last week, there was something that made the rounds, maybe everyone's seen it, sort of based on the previous like segment everything, you know, paper. There was somebody published a thing on GitHub or something. Maybe there was a publication that went with a 2 where they built on that, and it was a mat anything, right? So you give it a thing, you know, poke a couple of control points in the, you know, in the person or in the dog or in the object or whatever, and it like makes a map for you. It's a rough one, okay, but we wanted to try it out and see what it was like. But here's the thing, what it gives you is the final image, the matte image, right? Like, you know, like if you don't know what that is, like think of that as like, it's the black and white image that just is the segmentation of that object. It's surprisingly, like it's shocking how good it is at mostly figuring this out, but it's not exactly right. But remember what I was saying about the, like, sometimes it's super helpful to get to the 80%, but you're not at 80% if you've got that black and white image. That's the nothing percent, right? Like if you look at like the roto software that artists actually use, they're not painting the pixels. They're actually like drawing like spline shapes. And so if the output of this, you know, matte anything, instead of being the image, you know, the grayscale image that was the segmentation, if instead it was the control points of the, you know, the spline that captures the outline properly, that we can then edit to like fix the problems and, you know, animate it, you know, frame to frame and all that sort of stuff. Like that's a much more useful solution. And that's a more plausible, like, get us the 80% of the drudge work of setting up the shot and kind of getting it roughly done. And then we can fine tune it and, you know, put the actual artistry on top of that. And so this is my roundabout way of saying, like, reconceptualize some of what you think consists of solving the problem of, instead of being a final answer, being a human editable thing that they can pick up where the AI left off and take it the next step that they think is necessary to do.
All right, let's take some questions from the floor, please. Yeah, just get close. It should be fine. Okay, there should be a button on it.
How's that? Okay, good. So as you think about like putting this into a real pipeline, not just for prototyping, but really using AI in the artistic process, one thing I noticed is, yeah, we definitely need the ability to iterate and like say, hey, you made this thing, but change this property, change that property. That's happening with images, but I think 3D, maybe it's just getting started. My question though is, if you walk around a video game studio, I think you'll find a lot of
textures and meshes to represent a 3D world and 3D objects. And if you walk around CVPR, you'll actually see much fewer textures and meshes and more nerfs. I guess what I'm wondering is like, do you think there's any possibility of like is all this work here on nerf kind of just completely irrelevant to games and movies? Or is there a possibility of some new data structure that's more natural for AI to work in than textures and meshes?
Yeah, actually, that's an awesome question. So the question was, if I can sort of rephrase and understand that, is the work that's being done at CVPR, is it relevant to what we do in the industry, or is there ways that we should rethink in the industry and specifically in games to potentially, like, are we being inspired by this? I think. I walked the floor to take a look at the posters, and I'm kind of in hyper adapt learn mode while I'm down there. A lot of it's like way above my head, but I'm fascinated and interested with it. And I just had some like really interesting ideas. And you know, I don't know which poster it was, but one of the ideas that was that I was like, wow, I can really see how that could apply to games was segmentation that was occurring in an environment. And if I can kind of recall a little bit, it was auto-detecting soft areas that were in a room. It was auto-detecting metal objects that were in a room. And if I really think about what a character needs to, can a character now interact with that space? Can a character have kind of a novel conversation in that space and start to say like, oh, I really need to go sit somewhere and look around in the object for somewhere that's soft to sit. Now we can start to get some really incredibly different gaming experiences that are really weird and really novel and really customizable. I would love to see games head in that direction. Can consumer grade hardware do that right now? I don't know, a little bit. Will the PlayStation 6, the PlayStation 7, the PlayStation 8, will that hardware start to allow for those types of experiences to occur? I hope so. You know, those are the types of games that I would love. I would love to immerse myself in a world like Red Dead, but it's actually living and actually alive, and it's querying the environment. Like that would be phenomenal. And that's where I hope games start to head. So yes, the work that's being done here, I believe, is incredibly important to the work that we do.
Yeah, I mean, I think it's at the beginning, but I think the empirical answer to that is it's incredibly relevant. And the evidence that I would point to is my colleagues can't stop talking about it. Like we watch what this research community is doing, and just like in many ways, like can't wait to get our hands on it when it's a little bit more mature. But boy, are we watching it close. So like I think it's on the right track. I think it's extremely relevant to what we're doing. But I think, but we work at an industrial scale that is hard to explain sometimes. But just like how solid things have to be to survive the crucible of production.
And you have the momentum from your legacy code or your legacy projects, and the legacy way of thinking at your production studio. So it's hard.
Yeah.
Yeah.
If I can go to the next question.
Hi, Ben. Hi. Thank you for the insightful discussion. So I'm following up on that comment you just made. Basically, we can get about 80% of the way there with our current approaches. And to get to that high quality bar that we need for you to be very useful for you guys, in the demos that we get where they're very advanced, there's a lot of different prompting and recursive prompting approaches used to generate those demos. And my question is there a need for unification in these prompting approaches? And is that unification needed in order for you guys to be able to use this in major feature films?
Sorry, just as a it's just you don't realize until you're up here how incredibly echoey this room is, and it's actually really difficult to catch everything in the questions. So just if we act confused, that's probably why.
Yeah, I think I heard if there's a desire to unify how I guess text prompting might work. I actually just read a really interesting article on this the other day, and I think there's this term of like what is it, like prompt engineers. It's like it's a skill that people are starting to develop, and especially with technologies like Midjourney and others, where it's like you have to be so specific with what you're prompting to that thing. I think that's just an intermediate step of getting to that place where, we're humans, we use language to express ourselves. Sometimes we use, hand movements and other things. But I think, getting to that place where no matter what your input is, you can coax, a result that you're after. I'm hoping that we get to that point. So yes, I think the unification is necessary. I don't know if it's something that needs to be structured and aligned upon with, a bunch of different organizations, but I imagine that's naturally the place that we're going to get to, so that even users of our experiences can actually prompt something from their experience, no matter what language they speak or how eloquent they are with words.
Yeah, it's, even when it's a human at your beck and call, making the art for you, it's not easy to take words, let alone a sentence or a paragraph, and have it translate into the artwork that you thought it was going to be. Like that's why artists work visually, right? Like they'll sketch something, say, is this what you want? How do we refine that? So like some of the prompting that I'm most intrigued by are the multimodal ones, where it's a combination of the text and you do a sketch, or you provide, some examples, from other visual references, and these all together get synthesized into the thing that it's going to give you. And that, I just think that's so much richer than you're ever going to get from straight text, because it can be very difficult to concisely and accurately convey the visual and artistic concepts just through the words. Like you need pictures to talk about what kind of picture you want. And so things that can incorporate both the text and some sort of imagery, sketching, whatever, I think those are ultimately going to be more successful and more useful artistic tools, my guess.
Thank you. If it's okay, I will move on to the next question so that we can get through enough. Hi, Paul.
Hi there. Great panel, great workshop. Hollywood had a tough weekend, this last one, with both Pixar's Elemental animated film and the Flash visual effects live action film not doing well at the box office. I was wondering what your thoughts are for AI tools, maybe making it possible not just to make today's content more efficiently, but to make films and games that might be more likely to be things that people want to go and see.
Yeah, that's an interesting one. I don't know where I stand on that particular issue personally. I've been using these tools for on and off for about a year now, and one of the things that sort of concerns me about it is kind of that handoff of artistic control to the algorithms and the human element. And I sort of, I don't know how to say this lightly. Like I'm not a huge fan of the focus groups that are currently sort of mushing everything towards the same thing over and over again. And so can AI break us out of that pattern? Possibly. I would love to understand that. I'm not an expert in that problem, and I would love to see a solution to that problem. I worry in a world where ChatGPT, for example, is regurgitating the same 25 jokes over and over again, that we will end up potentially in a bit of a dark ages where some of the films, some of the games are samey, and we might enter a bit of a content desert. And I think as humans, one thing about being an artist, one thing about art and the sort of the human aspect of it is that there's a craving for the human experience and human storytelling. And as a director, as a film director, as a writer, we want to be able to share our experiences and have them resonate with other humans. And I think as we work towards a world where that's completely eliminated from the table is kind of a world that I'm a little scared of. And so I would like to see, instead of, hey, how do we make the Flash better? I would like to see something that's a little bit more, hey, can I hear a story from a completely different aspect of the world from somebody that maybe doesn't have a voice, that can now use AI to use tools to help get that story made. That's what I would prefer to see personally.
Oh boy, I'm going to step in it with this one. Some movies may be not doing great at the box office this weekend, but my movie's killing it. Well, no, I'm like, there's a luck of the draw part of it too. Like, you're in the middle of one of these projects and you don't always know, partly because, you don't always see the forest for the trees when you're deep in it. And sometimes there's just no accounting for what's going to resonate with the audience or not, whether you put your heart and soul into it or not. So like, I don't want to say like we always have the right answer, but I think, sorry, if you don't know, I'm talking about Across the Spider-Verse, right? Like that's the last movie we did. We're super proud of this. It turns out resonated with audiences. Successful also, but boy, are these things hard to do. And so things that can make people more productive, but not take away the actual artistic decisions that are being made that reflect, who we are as filmmakers and the skills of the artists that are going into it. I think like that's the combination that we're trying to triangulate our way to.
Thank you very much.
Thanks.
Hi, yeah, great workshop and great panel. Just trying to kind of like ingest all your feedback and tell me if I got it right. Would it be right to say that the level of the technology that you've seen, it's basically at a point that it's not so much more as a research problem, but it's more like how do you integrate it in your workflows? So it's almost like an industrial problem or a startup company problem. Take the technology, work with people like you, make sure that it exports to the right tools so that you can edit it. Maybe aside of like, maybe you said something about like full body animation. Yeah, maybe there is still a research topic in there. And then, yeah, I like your comment about how it's almost like you want to use like a meta language that is not just language, it's like a language that interfaces with the UI and with the actions that you would take in this software. So maybe that is a research problem, but everything else seems to be ready to be at least, pushed into production. That push is not going to be easy, but the technology starts to be there. Is that a correct assessment of like your opinion now?
Yeah, I think there's certainly going to be a challenge of productizing a lot of the research that's been done. Like there's a lot of really amazing technology out there. A lot of our workflows, like these guys have said, like we build on top of legacy content on engines that already exist that weren't necessarily designed for this type of technology, right? So integrating that into a long, complex workflow is not necessarily straightforward. So, definitely tons of value in having researchers on your team or researchers out in the wild that are doing all this amazing work. But there's still a lot of work to do to take that to an actual product that can be part of a pipeline, that can be replicated, that can be manipulated to create, great artistic content. So, yeah, absolutely.
There was a talk earlier today. I forget which one, and the speaker was saying, yes, like here's an array of examples where it works really well, but don't forget, like these were cherry picked from a bunch that didn't work out so well, and also like we're human, and so like we even subconsciously like we know the limitations of the system, and that sort of influences what prompts we're likely to give it. And that was really excellent work. But I think it sort of points to like the research isn't done yet either. So it's not like there is a matter of how can we take it and sort of productize it and put the industrial strength pieces behind it and figure out how to integrate it properly into the working pipelines. Like that's all true also, But I think there's more research to do too. Like, I don't think the work is done. There's a lot more innovation that needs to happen on the basic techniques. So like, yeah, don't think the research community is like, has it all solved yet.
Thank you.
Hey, y'all. Thank you so much for the time. Amazing panel, great workshop. I wanted to ask a little bit about the levels of controls that you guys are expecting from these tools. But let me know if there's too much echo. Right now, I imagine that you're using these tools, these generators with different levels of control to achieve a certain output that you think is correct, that you like, that follows certain style, etc. My research is more about understanding kind of cognitive dimensions of images and videos, and I'm wondering if you guys are interested or looking at in your work, kind of being able to modify or manipulate things like the perceived emotional content of the images or videos that you're generating or controlling or modifying. If you're interested in modifying the aesthetics, the general perceived aesthetics, the potential memorability, are those things that you guys are considering, interested? Is that something that you've thought about? Just curious.
Yeah, the style drop today, seeing that was like mind blowing, and like immediately through my head, I was thinking of all the applications. One of the working on the shooter project that I worked on for a number of years with Midwinter, one of the more difficult tasks that we had on that was trying to make all the materials look consistent and follow correct PBR guidelines, as well as it was slightly stylized. And we had to run through our texture library dozens of times and hand tune and hand tweak and modify those textures. And I think if and right now, if I use Midjourney, or if I use Stable Diffusion, or if I use any of the, number of the off the shelf image generators to make tileable textures right now, I don't always know what I'm going to get when I type in oak planks, tileable oak planks. Like it's going to arrive in a number of different styles. And so having that level of fine control to say, hey, I want this to be in this style versus this style, or here's a mood board. Here's like a big mood board of other, or here's a bunch of textures that we have there that we've kind of art director approved that are in that style now. Now work on these ones while you're referencing that, which is kind of what Dream Booth allows you to do. That's the type of level of control that I think would be very useful for me.
Yeah, I think just quickly, if you looked at any film set, like you watch a director and what they're doing on set, like the more not control, but direction that you're able to give to the performance of the people on stage, to the props, to the lighting, to every aspect of what you're trying to do. Think about how AI could help give you that control in an interactive way, or in a way, in post-production. It's like you've already filmed the clip, but you want a little bit of more emotion, like you said, out of that performance. And if you're able to manipulate that sort of stuff, I mean, any director would kill for more control, more ability to direct exactly what they're intending to see on screen, or whatever the medium is.
Thank you. I think we have time for 2 more quick questions. I'm sorry. So let's see if we can get through them. You should be able to tilt it. Just grab it. Yeah.
All right. Kind of pains of being short. Yeah, thank you very much for the very nice panel, and thanks for the organizers for actually getting art industry professionals here to kind of take academics out of the clouds, so to speak. Yeah, I guess this may not be necessarily an AI question, but so my research is in particular for traditional 2D animation. For example, traditional Disney, like classical Disney films, and the type of anime that comes out of Japan. And I'm really in love with the type of per frame artist care that goes into this, like as Larry previously mentioned. And I think that there may be a lot of applications, particularly from machine learning, to helping artists draw these. But I guess, at least in the West, it seems like everyone has moved more towards 3D pipelines, and kind of the 2D stuff has sort of fallen to the wayside. So I guess my question is, as people who have been in the industry for a very long time, why do you think this is? And do you see any way that we can change this trend? I would very much like to see feature films in 2D. There's not that many people doing them anymore.
I have a theory. I think, like, I hate to say it, but like, I'm a commercial artist. Like I make art for money, right? Like have to have a house to live in and support my family and so forth. So I make art for money. And I think a lot of these companies who came along and had the ability to do 3D or when the kind of the first notion of 3D films came along, people went to see them because they're novel and they're new. And they liked that newness of them. I think then people follow, where the money is. People go watch the movies, they make money. I can make another 3D film that makes money, and so on and so forth. And eventually, like 2D becomes, kind of the old way of doing things. And making a two-dimensional animated film is also really expensive. It's probably arguably as expensive as 3D in some cases. So I imagine, like, from the industry perspective, from a business perspective, I imagine there's a sense of people chasing what's commercially viable. But I think, to your point around how AI could potentially help that, traditional animation is an art form, right? And you look at compare it to blacksmiths, we have industrial machines that can make a set of knives really easily, but there's still people out there as artisans creating beautiful sets of knives by hand. And I think AI might bring back the ability for artisans who want to make a two-dimensional animated film, might make that possible again, because it's brought the cost down to a place where it's actually commercially viable for them to like pursue that project. But that's just my personal opinion.
Yeah, a number of years ago when, around the era when Pixar bought Disney, and that sort of revitalized the studio. And in that period, they did a few films where they tried to really get back to the 2D roots and had a really hard time making those like commercially viable. But I feel like they did an honest job at it. Like they really did try. And sometimes like audience tastes shift. So like when like I think it's what you said about like, ultimately like they have to do the things that make them money. Like I don't want to. That's not always as evil as it sounds, right? Like they can't necessarily control the tastes of the audience. Like they have their ups and downs, and there is a degree to which you have to make the things that people want to consume. But I think that the spark of hope there is that in the last few years, there is a revitalization of stylized looks in animated films. Now, they're not 2D hand drawn, right? Like, but I think that we've backed away from that. Like, there was a time that we were sort of in the mid like 2010s. Like, they were all starting to look kind of the same. Like we had the like better than just plastic. It looked, it was all like PBR plastic, but they had that, there was that canonical look that all the studios were sort of converging on. And now we've sort of re-diversified where there are a bunch more stylization and more artistic experimentation going on the animated film side. So I don't know, maybe the next one will be, much even more 2D, but I think we're seeing more of that like artistic look, and not just a realistic rendered thing. So yeah, who knows? Like it's a changing landscape, but I don't think that there's anybody sitting around saying like, oh, we're not going to give you this thing. No, like everyone's like trying to do their best coming at it from different angles, including the audiences. But yeah, there's kind of no accounting for tastes, I guess. Like people want certain things, and that's where the trends go. But it goes in cycles. So like, don't count it out yet.
Okay, last question for our panel.
Something that has been touched on a couple of times during the discussion, at least in the context of games, was the potential for AI to enable people to create really detailed, interactive, compelling worlds at really big scale. And something else that I know, another technology that there's been conversation around about being able to do that has been tools based on procedural modeling. As somebody who does research in both of these areas, both procedural stuff and machine learning, curious where you see the strengths and weaknesses of these two kinds of technologies in your pipelines and maybe ways that they could perhaps work together.
So I think your question was around like, can we see procedural content having a future in, I guess, building game experiences?
That's one way to interpret it. Sure.
Yeah, absolutely. I think you look at what people have been experimenting with like Netflix's Black Mirror, Bandersnatch, and kind of more interactive experiences as a whole. To be able to choose your own adventure, to be able to have a story that doesn't necessarily have a single ending or even 4 endings. It could have 1 million endings depending on choice that you make. I think that's a huge place where games are going to start to explore really, really thoroughly over the next few years. I know some games are already doing that, especially like giant open world games. That makes a lot of sense. But I think procedural content, even for things like vanity, being able to like create the human that you want to create in your game that looks the way you want it to look. I think that's really open-ended, and the ability to create procedural content to support that is possible as well. So yeah, absolutely. I think a lot of people are thinking about it now, and I think it's only gonna grow. And I think as people kind of broaden their horizon on what a game can actually be, now that we've got that technology to explore those things, I think your concept of what a game could be could even change.
Yeah, I think of Farmville, for example, and we had a style guide that we wrote for Farmville that had very specific rules for how buildings needed to be constructed, and the beams needed to be this high, and the stories need to be this big, and the windows needed to follow these specific rules. And through the years of developing that and working through the live service of the actual creation of that content, could we have kind of written some of that code in, let's say, Blender to automate the creation of buildings and give me a bunch of parameters, and I could say, like, give me a chicken coop, give me a barn, give me a goat yogurt factory. I was on this mobile project that I was working on more recently, exploring some of that, where it was a 2D game for the phone, and in Blender, I would create a very low fidelity manifold mesh with no texturing, no UV unwrapping, and then I was running that through, using that to then create canny, using ControlNet to create the canny outlines that I would then use to guide ControlNet and create chairs and furniture and props and buildings and stuff. And I was kind of doing this on my own, and I would a very, very small team, and I'd love to be able to extend that to a larger production, because I think the idea of procedurally generated content then being paired with AI to then create rendered content that is production quality, it's going to get done if it's not already happening. And I think the worlds that will be created using those techniques could be really, really compelling. So.
Thank you very much. Okay, unfortunately, the hardcore still in the room could go on for much longer, and we have to stop at some point. Please let's give a warm thank you to Larry, to Carl, and to Daryl. They'll still be with us if you have any last questions, but now is the time when we conclude the workshop. We have one last obligation, which is the poster session for the second set of posters. Again, these will be rated for the best poster prize, again sponsored by Google and NVIDIA. All posters are eligible. So we'll be heading over to the West Exhibit Hall to see those. Otherwise, we made it. Well done, everybody. Thank you all very much for your contributions to this workshop. It's been a pleasure. Thank you to all of our participants. Let's just do one more round of applause for everybody who has spoken and contributed to the workshop. I hope you enjoy Vancouver. I hope you have a good CVPR, and I hope to see you in 2024. Thank you all.